It's a pleasure to be here. I really appreciate the introduction or the opportunity to come down from Northern California and talk to you guys about these topics. So this session is about empirical Bayes and large-scale inference. I think it might be worth starting off with some motivation as to why such a topic might be of interest in a workshop like this. So the reason at least I started getting interested in these questions or these methods is that if you look across a lot of literatures in economics and actually other areas of social science as well, researchers are doing what you might call increasingly like drilling down on research questions to try to study heterogeneity and variation in finely grained unit-specific parameters. So what do I mean by that? A few examples from the economic sphere. So a classic question in labor economics is, what is the return to education, usually understood as the causal effect of an extra year of schooling on your labor market earnings or some other economic outcome. Over time, as we've seen kind of the progression of that literature and the availability of new, more detailed data sets, that's kind of morphed into questions about returns to types of colleges rather than just the year of education, more versus less selective colleges, as in famous work by Dale and Kruger, more recent work by Mountjoy and Hickman on the same topic. We see this kind of pattern of going from a kind of broad average causal parameter that everybody's trying to study to drilling down to effects of individual types of units or even individual specific units like particular colleges. So instead of a year of education as a whole or going to a more versus selective college, maybe we want to know what is the effect of going to Berkeley versus UCLA, something like that. Okay. And we see this pattern in other literatures, for example, in elsewhere in labor, there's kind of classic research by Kruger and Summers and others on industry wage premia. Do the same workers get paid more if they work in one industry versus another? The modern incarnation of that type of question is this recent literature on firm-specific wage premia. So do particular employers pay more to the same workers, not just industries, but actual specific firms? Likewise, in urban economics, we have classic work on the effects of neighborhood characteristics. What's the impact of growing up in a richer versus a poorer neighborhood? More recently, work by Raj Chetty and others is about effects of specific neighborhoods. So what's the impact of growing up in one county or even one a census block or something like that? Okay, and then we have this kind of growth of what you might call value-added studies in a bunch of different domains, both inside and outside of economics. These are studies that are basically about effects of individual teachers or schools in education, individual doctors or hospitals, other types of medical centers, managers, individual police officers, or judges. So what's the impact of getting assigned to one judge versus another on incarceration or other outcomes like that? These are all kind of questions about heterogeneity and parameters across a large set of individuals. And in settings like that, where we have many unit-specific parameters that are simultaneously of interest, empirical Bayes methods of the sort I'm going to talk about in this workshop can be useful for a number of different purposes. First, they can help us learn about the distribution of parameters across units. Once I'm studying a large population of units, there sort of arises this question: what does the spread of effects look like across those units? How different are the best schools from the worst schools? That's a question about a distribution of parameters. Second, these methods can help us improve estimates for individual units. This is sometimes called borrowing strength. So I reinterpret my estimate for one school, UCLA or Berkeley, in the context of a distribution of estimates across many other units that are similar in some relevant sense. And what relevant means, we'll come back to as kind of a theme of this workshop. And then finally, and relatedly, these methods can help us with making decisions. So policy decisions, if the goal is to decide which units to act on in some sense, maybe I'm a school administrator, I want to decide which schools should be restructured or expanded or closed. How can I do that? This is a natural framework for thinking about that type of question when I'm evaluating all the schools in a district, say. Or for us as scientists, what do we report? So it's not necessarily useful for me to print out a list of 1 million firm effects from a two-way variance decomposition into worker and firm effects. I don't want to make table 1 of my paper like 2 million lines, one for each firm. So what should I take? What summary statistics should I extract from that distribution of estimates to help my readers understand what's going on, and what's the scientifically relevant thing to report. Okay, so with that as like prelude, the point of this workshop is to provide an overview of empirical Bayes methods that aim to accomplish these various goals in these high dimensional settings and illustrate that with some applications. Okay, so I'll organize this in two different pieces. The first part you might call empirical Bayes basics. So I'm going to start with a very simple conceptual framework to be specific about what I mean by empirical Bayes, what's the model, what am I talking about, and develop a recipe for how this gets implemented in a typical empirical analysis. That'll lead us into discussion of linear shrinkage estimates and the James-Syme theorem, which are kind of a building block of this way of thinking, and why do we think these tools are useful. We'll then cover some other uses of empirical Bayes, combining multiple estimates of the same parameter, uses of empirical Bayes in a regression context. Maybe I want to relate parameters across units to some characteristic of the unit. How do I do that? And other forms of EV decision rules. This part will kind of end with a comparison to other methods that have a similar flavor that people might be familiar with, and in particular make connections between empirical Bayes and machine learning, which I'll show is in a sense the same thing, just with a different notation or a different kind of way of thinking about it. Okay, so that's part one. In between the parts, I wrote a little like coding lab for you guys to try some of these things out if you want to. We'll see how that goes, so we can spend time on that or not. The second part is like extensions of this basic recipe. We'll cover more flexible, generalized ways to estimate variation parameters across units. Non-parametric deconvolution, what does that mean? That means if I have noisy estimates for each of a bunch of units and I want to understand like nuanced features of the distribution of unobserved effects across those units, how do I do that? Issues of precision dependence, connections to multiple testing, which also arises in these contexts. Suppose I want to decide which, in the empirical example we'll do, which individual firms are discriminating against workers by race or gender, say, and how can I be confident about that? That's essentially a multiple testing problem, but it can be situated in this same empirical Bayes framework and help us think about the right types of tests to answer the question we might be interested in, and end with a variant of that, which is ranking problems. So suppose I want to rank the units. I want to make a report card about which schools are best or which neighborhoods are best. And I'm specifically interested in the comparison between the top ranked units and other units. How do I approach that in this framework? Okay, and then we'll have another coding piece at the end. And I'll give you guys the data from a recent audit experiment that some co-authors and I ran for large firms, where we tried to answer this question about which firms are discriminating more or less on certain dimensions, and you can see what you think of that. Okay, so that's the outline. I didn't make any announcements about the format. You guys should feel free to ask questions as we go. It's probably more interesting than hearing me talk uninterrupted for a couple of hours. So feel free to ask questions or make comments. But if there's no questions to start with, I'll just get into it. Okay, so I'm going to start with a basic conceptual framework to formalize some of the ideas that I talked about on the last slide, and illustrate this with a running example that's close to some of my own work on educational effectiveness. So let's think about an empirical scenario where we have a set of groups indexed by J. So these might be schools. Okay, there's some group variable. And then we have individuals that are nested within those groups in some way, indexed by I. So these would be like students. So I have a data set that has a bunch of students in it. Each student is attending some school, and it's a nested data structure with every student in one school or another, multiple students per school. All right, and then I get to see an outcome for every unit I in each group J. So I'm numbering the units separately by group. So Yij is the outcome of interest, like a test score for individual I within group J. So I is running from 1 to nj, maybe the schools are of different sizes or something like that. Okay, and then there's some unknown parameter, call it theta j, that I'm interested in for one reason or another, that determines in some way the distribution of those unit or individual level outcomes Yij. So you could think of this as the effect of school J, or at least the mean test score at school J, something like that, some parameter of the distribution of Y specific to that school. So simplest possible example, suppose test scores are normally distributed, homoscedastic, so they have the same variance at every school, but they have a school-specific mean. So every kid's observed test score is like the mean for their school. You could, if kids were randomly assigned to schools, that might be a causal effect of the school. Otherwise, we could just think of it as an average, and then idiosyncratic error within school. And the conditional on the group level parameter, meaning the idiosyncratic piece that's not explained by school, let's just make that normally distributed with a common variance. Okay, so empirical Bayes recipe, what we're going to do in the first step is to start by forming an estimate using the data specific to each group. So we'll call that theta hat j is an estimate of theta j. In the simple school effects example, the natural estimator to think about here is the sample mean for every school. So I have capital J schools. I'm going to compute the mean test score at every school. That's my theta hat. This is just the formula for a sample mean. And I want to think of those theta hats as unbiased, but noisy estimates of the group level parameter theta across the groups. So in the very simple case where we have normally distributed noise in the student level test scores, the sample mean is finite sample normal centered at the true mean, and it has a standard error. The standard error in this case is just sigma squared over, or the squared standard error is just sigma squared over n. So that's just the variance of a sample mean, right? So I take the mean for every school. It's a noisy estimate of the real mean at that school, and it has variance sigma squared over n. Okay, so that's just like basic statistics. That's step one. Where things start to get interesting is when I start to think about what's going on across the groups. Okay, so within every school, I have theta hat, normally distributed, mean theta, variance sigma squared over n. But what I'm interested in next is, are the schools different from each other? How do those means vary across the schools? And we'll formalize that idea by modeling the thetas, the group level parameters, as draws from some distribution G. And we're going to talk a lot about G. What is the meaning of G? But for now, let's just call this distribution G. That's what we'll refer to as the mixing distribution, for reasons that will become clear going forward. This is kind of the basic animating object in empirical Bayes analysis, is the mixing distribution. And we're thinking of this as an objective feature of the world, not a subjective prior. Okay, that's important. So much of what I show you is going to have a Bayesian looking flavor. I'm going to end up using an estimate of G as my prior, but it's important to emphasize that in a model like this, G is a feature of the world. It tells me about the distribution of quality in the set of schools that I'm studying. It's not something that I came to, that's my subjective prior. It's a fact about the world, okay? And in particular, it answers questions about variation in parameters across the units that I'm studying. So, stick with the school effects example. Suppose the J is indexing schools within a district, and you could ask me the question, how much does quality vary in this school district? A sensible answer to that question would be, well, what's the variance of the average performance of students across schools? That's a feature of G, sigma theta squared. That's the variance of G. It's the variance of the group level parameter distribution. Okay, another twist on that question, what's the difference between the most and least effective schools, say the 75th and 25th? That's another feature of G. It's the 0.75 quantile minus the 0.25 quantile of that mixing distribution. So step one of the EB recipe was to form these group level estimates theta hat. Step two is to use those estimates, along with what we know about their noise, their standard errors, to do what's called a deconvolution and extract an estimate G hat of the mixing distribution using the noisy group level parameters theta hat together with their standard errors, which we're calling Sj squared here. Okay, so we're going to go forward with that, but you might already be uncomfortable with some of the things I'm saying. This looks at kind of like a random effects model, which in your econometrics training you might have learned is involves strong assumptions, or is like something that we don't like to do. So what's going on with this? What's the philosophy behind this type of modeling framework, and why should I adopt this view that the parameters that I'm studying across schools are draws from or like a random variable drawn from a distribution? Okay, why should we do that? The alternative perspective is a fixed effects perspective, which says, okay, I have J schools in my district. They each have a parameter, a mean. I don't know those means, but they're just a list of numbers. Theta J running from 1 to j. So what does it mean to say that those came from a distribution or they follow a distribution or something like that? One answer I could give that's sometimes works but is often unsatisfying is that maybe the units I'm studying were sampled from some larger superpopulation. So I could have done a multi-site randomized trial or something. Theta hat is the effect of a treatment at a particular site, but there are many other sites I could have drawn, and I don't get to see those. So the sites that I drew are kind of coming from some broader population characterized by a distribution. In other cases, it's not so clear that we should think about things that way. If I'm studying a school district in the US, where are the schools that could have existed but don't exist? Where are the US colleges that I could have sampled but didn't sample? Maybe I have data on all the colleges. So the superpopulation view is not necessarily compelling in all cases. Instead, what I'd like to argue or emphasize in this lecture is that this random effects view can be motivated not by like a literal view of the world as working that way, but instead by your objectives as the statistical or econometric analyst. So even if we're dealing with a finite population of units, I just have a list of schools in my district and I see all of them, I can think about the thetas following some empirical distribution in that population. And I can sensibly ask questions about that distribution. And it's going to turn out that if my objective, if the loss function that I'm seeking to minimize as an analyst cares about how I do on average across all the units that I'm studying, I'm going to do better by adopting this framework and thinking of the thetas as having been drawn from a distribution as random effects, regardless of whether that's true or not. Even in a pure fixed effects world, the procedures that come out of this view of the world perform better than treating each school in isolation, even from a pure fixed effects frequentist type perspective. Okay, and with that as motivation, we can sort of think of the continuous or IID random effects models that we'll sometimes use for G as parsimonious approximations that we use in service of frequentist goals rather than taking this random effects view as a literal description of the world and how it works. One thing this discussion is not about, last philosophy point before we move on, this random effect versus fixed effects discussion, this is not about whether the thetas are correlated with something observed or not. You might remember from Econometrics 1 that like in panel data, random effects is the one where I assume that the thing is independent of X and fixed effects is the one where I don't. That's not what I mean by random effects. What we're going to be working in this the framework here is what you could call a correlated random effects model, where I think of the thetas as drawn from a distribution, but I'm not putting any restrictions, at least not yet, on what they are or are not correlated with. It could be that the thetas are correlated with student characteristics. It could be they're correlated with anything. That's not what this discussion is about. Okay. Any questions about the philosophy of this before we move on? Okay. Yeah.
Are we still relying on averages here? Is there any way to talk about the individual students in effect, or?
So I'm kind of taking it as given that the parameters of interest are living at the group level. Applications of this arise, you could equivalently think of this as if I was estimating a heterogeneous treatment effect across students or something, the J could indicate student subgroups, and I want to know how the effects vary across those groups or something. So this is really about any scenario where there's a grouping structure and I'm interested in a distribution of parameters across groups. The parameters for individual students in a model like this are kind of hopelessly unidentified, kind of because of the fundamental problem of causal inference. I could never hope to learn the effect of sending you specifically to UCLA versus Berkeley, but I might be interested in averages of that effect across some groups or the dispersion in those averages. That's what this is about.
So yeah, say I don't care at all about the unit specific effects. I just want the distribution G. Is there any reason to do this like two-step approach as opposed to like, say, just starting with correlated random effects? Like, are you going to get something different if you, take some approach that you just estimate that distribution G directly?
Well, we're going to estimate the distribution G. That's the next step in this. There are different ways to do that. Maybe you're proposing.
Well, as opposed to getting a bunch of theta hats and then getting G from that, is there a way to just get G directly from?
So like in this model, we have a fully parametric model for the microdata. So you could do one-step maximum likelihood and it will tell you an estimate of G, which will typically be a slightly different estimate than the simple thing I'm going to do. There I'll talk more about this as we move out of this toy example, but you kind of have the classic trade-off between robustness and efficiency. So if you have a fully parametric model for everything, including the microdata, that the maximum likelihood on that is going to give you the efficient estimate, including of the parameters of G. Normally, when we actually do this, I'm going to think of this assumption here that theta hat is normal, centered at the truth with this variance that I know. I can appeal to like a central limit theorem argument for that rather than believing an exact finite sample normal distribution for the microdata. And we'll have the kind of folk wisdom that two-step is less efficient but more robust typically than one-step fully parametric maximum likelihood. So that's, I think, often why we do this. In practice, I'm not going to believe that this is literally true, but I think it's a decent approximation. And I don't need to take a specific stand on what's going on in the microdata as long as I have a decent estimate of the sampling variance of each theta, and it's roughly hitting its normal limiting distribution. Does that make sense?
Yeah.
Yeah.
So in terms of interpreting that as heterogeneous treatment effects, in this setup, do we still need a clear control group and treatment group, or everyone can be treated?
Well, so this is sort of fully separable from whatever research design or approach you think you have for estimating the individual thetas group by group. So those could be treatment control differences separately for each of a bunch of groups. They could just be averages. They could be anything that varies across groups. And I'm taking as given that you're interested in those for some reason. If you have a research design with no control group, probably the thetas that underlie that research design, don't mean very much. And that's going to be true in any study without a research design, whether I'm doing it for many groups simultaneously or just one group or whatever. So this is just about what I'm modeling here is about the distribution of thetas across groups. What you decide you want your theta to be, that's kind of up to you. This isn't helping you with that. Okay. All right. So moving on from the philosophy, and let's move forward with this random effects framework. In the school effects example, let's stick with that, and let's just go fully parametric for now to start with to illustrate the method. And suppose G is also a normal distribution. So it has a mean and a variance, but once you know that, that's all you need to know about it. It only has two parameters because it's fully parametric, it's normal. Then what I'm working with is this hierarchical model right here. I have a theta hat for every group. It's centered at the true theta and has a sampling variance that I know, Sj squared standard error. And then at the higher level, at the group level, the thetas are also normally distributed. They have a mean, mu theta, and a variance, sigma theta squared. And I'm writing that conditional on the standard error. Okay, why am I doing that? Well, in principle, actually, this distribution could vary with the standard error. It could be that the schools with more kids in them are better, or something like that. So it could, in that case, I would have more precise estimates for the better schools. I'm kind of ruling that out with this simple model here. We'll come back to generalizations of this that allow that kind of dependence. But in general, we're going to have to take a stand on how the precision of our estimates relates to the truth in order to make progress on at least some of these questions. I'm going to take the simplest case and assume independence of that for now. Okay, so in this world, the group level distribution just has two parameters, mu and sigma. We call those hyperparameters. Okay, why hyper? Well, they live at a higher level of the hierarchy than the individual group parameters theta j. They're parameters of a distribution of parameters, right? They're describing how the thetas vary, so they're living at a higher level. Hyperparameter is a shorthand for that. So with this model, what I was calling deconvolution, meaning extract an estimate of G from the noisy theta hats and their standard errors, that's just a fancy way of saying I want to estimate these two parameters because that's all there is to G. So once I know those, I know everything. How should I do that? There's different ways to do that we'll talk about as we go. Simplest possible way is just like a very basic method and moments type of procedure. How do I estimate the mean of the distribution of thetas? Well, I can take the mean of the theta hats. Each one is unbiased for the individual theta. So this is going to be an unbiased estimate of the mean of the mixing distribution. My estimator for the variance of the mixing distribution Remember, this is like the dispersion, an estimate of the dispersion inequality across the schools in my district. That's going to be the sample variance of the theta hats that I get to see, minus the average squared standard error across the schools. Why am I subtracting the average squared standard error? That's a bias correction that accounts for the fact that the theta hats are excessively variable relative to the true effects theta due to sampling error. So even if all the thetas were the same, all schools are identical, you compute sample means in your data, you're going to get some spread in the theta hats by chance. How much? Well, you know your standard error, so you kind of know how much to expect. The answer is the average squared standard error. So this is a very simple bias corrected variance estimator. We'll talk about more elaborate ways to do that later in the lecture. So if I find that this estimate of the variance of the mixing distribution is big, we have what's called overdispersion in the theta hats. That means they're excessively variable relative to what we would expect from pure noise if all the groups were the same. Okay, so this is an index of how overdispersed are the theta hats relative to their sampling variances. You know, as we've already talked about, actually, I could take other approaches to estimating this. I could do one-step maximum likelihood if I had a parametric model for the microdata. I could think about precision weighting these formulas. So, you know, the theta hats have different variances. Maybe I want to weight by 1 over the squared standard error or something like that to take account of that. That relates to the precision dependence issue that we discussed on the last slide. You know, if the weights in that formula, if the standard errors are related to the true effect size, then weighting is going to change the estimate, actually. So we'll come back to that idea. So we'll start with this very simple one, but there's other ways to do this hyperparameter estimation step. Yeah.
I may have missed it, but the errors are assuming it's null, right? But what if I have to estimate it?
We have
a problem for this bias correction?
not necessarily. So when we do generalized variance estimation, it's going to turn out that a degrees of freedom corrected version of this will be unbiased for sigma theta squared as long as S squared is unbiased, even if it's noisy. So for some purposes, it's going to make this a noisier estimate, but it doesn't create bias in the variance. In other cases, noise and the standard errors will mess you up, and we can talk about that later as well. But for now, we're treating them as known. Yeah.
Is this bias correction informed by the shape of distribution G? I would specify not normal G. That do a different bias correction.
So there might be a more efficient estimate for the variance if you knew more about the shape of G, but this one is going to work regardless of what it is. So that'll also come up in this generalized variance estimation thing. We can get the first 2 moments of this without taking a stand on what G looks like. If we just care about this first and second moment, that's estimable regardless of what the higher moments look like. Yeah.
Sorry, I'm a little confused. We're expecting the variance parameter to be negative after like the estimate for the variance parameter?
No, I'm not it could be negative, actually. I'm not imposing, so if I did maximum likelihood, that's imposing all the constraints, it wouldn't be negative. This simple estimator could be negative, actually. What would that tell me? That would tell me I don't have much over dispersion. And actually, I have less dispersion than I would expect due to chance. So you could find that in a sample that would tell you probably actually the groups are kind of the same. That's one way to interpret that. And so what I'm expecting if I thought there's a lot of variation in school quality is this number to be positive. This number, if I took this out, has to be positive. It's a sample variance, but I'm taking off the part that I think is due to sample variance. So whether that's going to be 0 or positive or slightly negative, I'm not sure. It depends on the real signal variance.
But then, so I shouldn't really treat it as being an actual variance. Like I can't plug it into a distribution, have a negative variance.
Yeah, so this will come up in the variance estimation part. A slightly more defensible estimate of this might be max of this and 0. So that's something people often do. That's no longer unbiased for the variance, actually. You know, if I want an exact finite sample unbiased variance estimate, I have to typically tolerate the possibility that it'll sometimes be negative and nonsensical. Because I want it to be unbiased even when the truth is 0. So we're doing this because we're kind of looking for unbiased variance estimation, but you might dislike that property, and so you can do at the cost of some bias, you can impose that type of constraint. Yeah.
So when you got that your sigma hat square is positive in both the dispersion, Is that the same as a test that there is heterogeneity? Is this the same as rejecting the null of non-heterogeneity?
So I'm not doing inference on it yet, but it's very closely related to that. And in fact, in some cases, the test statistic for a test of the joint null that all the thetas are the same is essentially going to be like proportional to this. And when this number is big, you're going to reject that. Yeah, but to do a formal test of that, there's various ways to do that. I could put a standard error on this. It's going to involve fourth moments instead of second moments. So I can do that.
Correct.
If the real, this is getting increasingly arcane, but if the real sigma is close to 0, a walled test based on a standard error for this is not going to perform well because it can't actually be normally distributed. So, there's different ways to do it. All that's going to come up in the variance estimation part, but your intuition that this is essentially checking whether all the thetas are the same. It's a statistical check for that. This is a point estimate of how different they are. That's correct. All right. So that's step 2, basically. Step 1 of our recipe was to estimate the thetas. We get our theta hats. Step 2 is to do deconvolution, which in this very simple, normally distributed example just means estimate the mean and the variance of the mixing distribution. Step 3 is shrinkage or formation of posteriors. Okay, so this is going to be about refining the estimates for each individual unit in view of what we've learned about the distribution that we're dealing with from the deconvolution step. Okay, in the simple normal model that I've been working with so far, this works out especially easily. Suppose starting out that I actually knew the parameters of the mixing distribution, didn't have to estimate them. So I know sigma theta and mu theta. What is my posterior mean for theta in this random effects model, given the theta hat that I see? This should also be conditional on S squared, really. But given the estimate that I have and what I know about its variance, and the fact that I know it came from this distribution G, what's my best guess in a posterior mean sense of this individual theta? It's this formula right here. Okay, so this is the basic linear shrinkage formula. This is a weighted average of the noisy theta hat and the mean of the mixing distribution, where the weight depends on the signal to noise ratio in the estimate that we have. Okay, so if it's very noisy, if Sj squared is large, I'm going to be putting increasing weight on the prior mean as my standard error goes to infinity. I didn't learn anything from theta hat, so I just get back mu theta. As my standard error gets small, I put more and more and more weight on the estimate that I have for that group. And as S goes to 0, I end up with theta hat again. Okay, because in that case, I know theta. All right, so this is a shrinkage formula. This linear shrinkage posterior mean pulls the noisy estimate theta hat towards the prior mean based on how noisy it is and the underlying signal variance, the variance of the mixing distribution. We got this formula from normality, but it's going to turn out that it has good properties regardless of what G looks like, regardless of whether G is a normal distribution or not. The intuition for that is that this theta star object is the fitted value from an infeasible regression of the true theta on theta hat. So if you told me the real thetas and I had my theta hats and I run a regression of theta on theta hat, this is the fitted value that comes out of that regression. And therefore, that fitted value is going to have all the usual properties that we like about OLS regressions. It's a best linear approximation to the real posterior mean if that's some other more complicated nonlinear thing, because G is not normal. Okay. So as written, this formula is not feasible because I actually don't know when I go into my study what sigma theta and mu theta are. I had to estimate those. In fact, I did that on the last slide. So the empirical in Empirical Bayes just says, let's do a plug-in estimator where we stick in the deconvolution estimates of those parameters of the mixing distribution and then act like that was our prior, like we knew that, and form the empirical posterior mean using that information. So this differs from the last slide. This is theta hat star rather than theta star because there's hats on the sigma and the mu. The G that I'm using now has a hat on it because I estimated it by deconvolution. Yes?
In practice, to have confidence on this, we need to have a fairly large sample of groups. Is that right?
Well, it depends on what you mean by confidence. I'll show you that actually to guarantee an improvement over just theta hat in a particular sense, you only need 3.
Oh, okay.
But it's obviously going to do better and better and better. It's going to get closer to what's sometimes called the oracle posterior. The oracle posterior is what you would get if you actually knew these and didn't have to estimate them. As you get more precision on the hyperparameters, you're going to get closer and closer and closer to that because these are going to be so converging to the truth.
But this works well
But-
in a very small number of groups.
It's guaranteed to give you an improvement in mean squared error in a particular sense that we'll talk about in 2 slides. Okay. All right, so this is the simple empirical Bayes linear shrinkage formula, but this is a reflection of a much more general idea in empirical Bayes analysis, which is to use a deconvolution estimate G hat of the mixing distribution as your prior when forming posteriors for individual units. So you can apply that principle with more complicated models for G, with more complicated functionals of the posterior. Maybe you care about some other decision or feature or quantile or something, not the mean, but you can use the same approach, plug in estimate of G, figure out what feature of the posterior you care about, estimate G, stick that in and use that. So that's empirical Bayes. This has various creative names in the literature, traditionally called borrowing strength from the ensemble. That comes from Efron and Morris. So I'm borrowing strength in the sense that I used all of the schools in my data set to estimate the hyperparameters. And I'm using those to refine my estimate for each individual school. So I'm borrowing strength from the others when I do that. Sometimes called using indirect evidence from the other schools when interpreting the estimate from one school, or learning from the experience of others, which Efron calls it that in this 2012 book. Sounds like a nice thing to do. Okay, so that's the basic empirical Bayes recipe. We have this 3-step formula: estimation, estimate a parameter together with the standard error for every unit. Deconvolution, use those estimates to figure out what's going on with the distribution of parameters at the group level. That's your G hat. And then shrinkage, treating that as your prior, update based on the estimate for that group. So prior plus data equals posterior, and the shrinkage part is these posterior predictions for every unit. Yes.
Is this deconvolution step where we need to specify like a prior mixing distribution?
So that's where you estimate G. Like I said on this slide, you can do linear shrinkage even if you don't want to take a stand on what G looks like, because of this best linear fit type of argument. You're still going to get something that's a best linear approximation to this object here, even if G is something more complicated that you don't know and aren't willing to take a stand on. We'll talk later about how to estimate more complicated G's if you are inclined to do so, but linear shrinkage is actually going to work well regardless usually.
I'm just saying that that's where the step where we need to specify a G. Like even if we don't necessarily believe a G, like we have to take some stand in order to do this deconvolution step.
Yeah, to do linear shrinkage, you only need to assume G has a mean and a variance, and you estimate those here. Because that's all I need. And then but this is where I'm dealing with G in some sense. Whatever I want, I'm willing to assume about it. Yeah.
So you get a new kind of preferred estimate of the treatment effect for each unit. And then I kind of want to say, what's the standard error of that? Is it significant for this unit versus that unit? So that is there a step there in the shrinkage where I estimate the stand, like?
So standard error on that is, do we want to do that or not? As we're going to talk about on this slide, it's a biased estimate now. So it's not centered, conditional on the parameter for that unit. It's no longer centered at the truth. I sacrificed unbiasedness to reduce my variance when I did shrinkage. So putting a confidence interval around it that's centered at that point doesn't actually totally make sense anymore. You can do empirical Bayes confidence intervals. So Armstrong and Colasar have an interesting paper in the AER a couple of years ago about how to do them, sort of putting confidence intervals around these guys in this empirical Bayes type framework and thinking about frequentist properties of those. So you can do that. But normally the way you would think about this is an improved point estimate. If you're trying to do, that's a different question than how would you do inference on that parameter. So we'll talk later about the multiple testing thing. You know, do I want to decide if it's 0 or not? If that was what I actually wanted to decide, I would do something different than this. I would probably use a different feature of the posterior actually. And we'll get into that. So this one is about mean squared error, as we'll talk about now. It's like estimation, better estimate. So that's a natural transition actually to this slide. Should I prefer the shrunk posterior estimate that I just described on the last slide to the unbiased estimate theta hat? You know, I thought I learned in introductory statistics that the sample mean is a good estimate. Now you're telling me not to use the sample mean. Why would I do that? What's going on? Okay, well, it turns out that actually it's not obvious that you should prefer the shrunk prediction. It depends on what you're trying to do as the analyst. To make that point, let's just continue to stick with this toy model, everything normally distributed. Theta hat is normal, theta s squared. Theta is normal, mu theta, sigma theta squared. And let's stick with that model and think about a mean squared error criteria. So suppose my goal is to get minimum mean squared error. And let's condition on the theta for the school we're looking at right now. So suppose I only care about school number 1. It's the school in my neighborhood. I don't really care actually what's going on at any other school. I just want to know if that school is good or not. The formalization of that is to say condition on that theta. For now, we're focused on that theta. What is the mean squared error of the unbiased theta hat versus the shrunk? Sorry, I'm missing, importantly, a star on one of these. Yeah, this should be theta star right here. Okay, what is the mean squared error of the unbiased estimate versus the shrunk posterior mean? Those are given by these formulas here in the normal model. The mean squared error for theta hat is just its squared standard error because it's unbiased. So MSE equals variance. What about theta star? Well, it now has a variance component and a bias component, a squared bias component. I shrank theta hat towards a constant. And so in general, that makes it a biased estimate. Now, it was unbiased before. I moved it towards some other number. It's now biased, conditional on theta. So I have 2 pieces to my MSE. The variance has gone down because the constant is not as variable as the theta hat. So I've reduced my variance by shrinking towards any constant. But I have a squared bias term that depends on how different is that theta from the mean, the place that I shrank it towards, actually. So if I'm moving this theta towards the mean, and it turns out that the school in my neighborhood is actually very atypical, it's very far from the mean, I've probably made things a lot worse by doing that. Okay, and in fact, if I'm only interested in one school, it's not clear which of these is better. It could easily be that this is bigger than this if theta minus mu is big. And that bias is not uniform in the true parameter. So the more atypical is this school, the bigger the bias contribution to this shrinkage MSE formula is going to be. And with an unbounded mixing distribution, actually, this is unbounded. So my worst case MSE for this estimator, conditional on theta, is infinite. So maybe I'm uncomfortable with that. If I care about worst case MSE, probably I'm going to stick with the sample mean, actually. I only care about one school. This is kind of an illustration of the principle that, like, you can imagine an econometric estimator that is the number 4. Okay, that's an estimator. If it turns out that theta is close to 4, that's a great estimate. But maybe it's not. And I want to insulate myself against the case that it's not if this is the theta that I care about. And so maybe I use this instead, right? Because this one has bounded MSE for any theta. Okay, but now suppose I'm interested in a different problem. I don't just care about the school in my neighborhood. I care about all the schools. I want to produce a list of estimates that does well on average across schools, not just for any one. In this random effects framework, the formalization of that is to integrate MSE over the distribution of thetas. So imagine you're in a world where you're repeatedly asked to evaluate schools in this population, and you want to do well on average across all those evaluations. Okay, that's integrating your MSE formula over G, which is the distribution from which those thetas are being drawn. That doesn't change anything for theta hat because its variance is S squared regardless. But for theta star, the posterior mean, we average that squared bias contribution across values of theta, and it turns out that MSE is this, which is just S squared times the shrinkage factor, which is less than 1. So this actually has to be better than this. So the unconditional MSE of the shrinkage estimator is below that of the unbiased estimator. That means that if I want an estimator that does well on average across all schools, the shrinkage estimator dominates. Okay. And this is related to the James Stein result, which we're going to cover next, that it turns out the sample mean, or more generally, the maximum likelihood estimator is inadmissible under an MSE criterion and dominated by this type of shrinkage estimator, as long as I'm estimating at least 3, which was where my answer earlier came from. So this is that result in this random effects, everything normally distributed framework, but it turns out that that applies much more generally. Let me show you that next. So this is the James Stein theorem. Let's get rid of the random effects framework for a moment. So suppose you want to throw that out. You don't like random effects. You don't know what I mean by the thetas were drawn from G. The thetas are just a list of numbers now. Just like in any econometric problem, we want to estimate those. But we're going to assume we have at least 3 of them. And let me, to make the math simpler to see, let me just assume that the standard error on each one is 1. So maybe I've z-scored them or something before I do this. That's not going to be crucial. I can generalize that later. But let's suppose the standard error is 1 for each unit. So I have a bunch of thetas, at least 3. They all have standard error 1. They're centered at the truth, but I don't know what the truth is. And I want to choose an estimator that has good total MSE across all J parameters. So I don't care just about one of them. I care about my MSE summed over all capital J, where J is at least 3. So I would like to do well on this criterion here. Because the standard error is 1, the MSE of theta hat, just like before, that's just J, because it's 1 for each unit. So that's what I get if I don't adjust my thetas. And now let me give you a different estimator. Should look a little bit familiar, called the James Stein estimator, which is shrinking theta hat towards some constant m. Could be any constant, actually, you pick it. Pick whatever you want. Could be the number 4, as we just said, or it could be something else. And the shrinkage factor is this thing right here, which depends on the sum of squared thetas relative to m. It's kind of the average squared distance of theta from m across the different thetas in my sample. So I'm shrinking the theta hats toward a constant using the sum of squares shrinkage factor. And it turns out that it's a theorem that the MSE of that summed over the J bigger than or equal to 3 schools is below the MSE of the unadjusted theta hat. That's a theorem, okay? There's no random effects here. There's no normality of G. There is no G. There's normality of this noise here. So I kind of have to believe that for this to work. But this could come from anywhere. This is just an alternative estimator that I'm proposing, and it has better MSE. So why does that work? Well, it should be clear from what we said before that that estimator is an empirical Bayes shrinkage posterior mean that's motivated by a normal prior mixing distribution for the thetas. So if I thought the thetas were normal and centered at m and I think I know m, but I don't know the variance and need to estimate it, my shrinkage factor should be 1 over 1 plus sigma squared. That's my signal to noise ratio when the noise is 1. And it turns out that this thing right here is an unbiased estimate of that. Okay. And so I get an unbiased estimate of my shrinkage factor. You need J to be at least 3 to get an unbiased estimate of that shrinkage factor. But as long as you have an unbiased estimate of that, your MSE goes down. And it doesn't require anything Bayesian, nothing random effects. That's a pure like frequentist type of result. Okay. And I gave you this in the toy example, but this generalizes to having standard errors that I have to estimate that aren't the same, not equal to 1, and so on. So the point of this theorem is that we can often think we're going to work with this type of mixing distribution model, but we can often think of that as a device that motivates procedures that are going to have good frequentist properties, even if it's not literally true. James Stein theorem tells us that it works, even if this model that I use to derive that estimator is wrong. Okay, but what I did need was a loss function that cares equally about at least 3 parameters. So that's really where the rabbit goes into the hat with this. I need this kind of compound loss function where I'm trying to do well on average across all the units. I'm going to make some things worse for some units and better for others. All this tells me is that on average, I do better. It doesn't tell me that I do better for anyone. Yeah.
So you use the word caring. Can we formalize that as perhaps a weighting? That like, as long as you have 3 items and the weight you put on all of them sums up to 3, if you care about one a little more, that's still okay? Or
So I could do a version of this where I put a W in here. That's actually fine. You just tell me that now you care about W theta. That like theta tilde equals W theta, and then it goes through. I just have to care about all of them. Okay. So if you're trying to apply this type of logic outside of this compound decision framework where we care in some sense equally about doing well on average across a bunch of units, then this can quickly get you into trouble and lead to some absurd conclusions. So, I'm a labor economist. I read papers that report elasticity of labor supply or return to schooling, or maybe an intergenerational income elasticity. Should I shrink my estimate of the elasticity of labor supply towards my estimate of the return to schooling? That doesn't really make sense. I don't do that when I think about different literatures. The reason for that is that my loss function, when I'm thinking about those parameters, doesn't really look like this. It's not a compound decision problem. There's no like well-defined decision that depends in some sense equally on those things. So I really have to think the units are similar in some relevant way that makes me care about doing well on average across them in some decision problem in order to justify this type of shrinkage procedure. But in these value-added studies where I have a bunch of teachers or a bunch of schools or a bunch of subgroups or whatever, it's kind of natural to think about it that way. Why would I specifically care about the labels on the individual units? I want to know about the distribution, and I want to report estimates that do well on average across those units. So that's why these methods are useful in those scenarios. Okay, so I'm going to show you a slightly more involved version of this school value added thing just to illustrate the logic of these methods in action now. So we were just doing simple means before, but now let's think about estimating causal effects of schools. This is drawn from this paper about school value added in Boston. And let's go to like a causal potential outcomes framework now and see how this works. So think about capital J schools in the district, and now I'm thinking about causal effects. So I have a potential outcomes model where each student I has a potential outcome yi of j that would obtain if that student were to attend each school j. So I have a potential test score I would get if I went to school 1, school 2, school 3. And let's take a simple additive potential outcomes model where it's constant effects. So everybody's potential outcome is a school effect plus an additive person effect, which means that the effect of moving any person from school 1 to school 2 is constant. It's just the difference in these theta, as we call those school value added parameters. Okay. This A thing, that's like all the other stuff about a student that affects their outcomes that's specific to them. It could be family background, other prior human capital investments, whatever, student heterogeneity. So there's several questions you might care about in a study like this. You might be interested in the value added of a particular school, like the one in your neighborhood. You might care about features of the distribution across schools. So is there a lot of variation in school quality in this district? And you might be interested in making a decision that depends on the thetas. Which schools should I select? Which schools should I expand? Which schools should my kid go to? That kind of thing. Okay. So empirical Bayes is going to be helpful for us in answering those questions. Although, as we saw for the first one, it's a little subtle. And in fact, if I only cared about that one, maybe I wouldn't want to do this. So how do we proceed? Well, this is a causal inference problem. The observed outcome that I get to see is the potential outcome associated with the realized treatment choice. So I can write the observed y for a kid like this. It's a sum of school dummies times the value added for that school plus their own individual heterogeneity term. Probably we don't think people are randomly assigned to schools, so we're going to control for a bunch of stuff to try to get rid of selection bias. Let's call those covariates X. So think about projecting the student heterogeneity term A onto X. That gives me a model that looks like this, where epsilon, the residual from that projection, is uncorrelated with X by definition, but might be related to the school attendance dummies because these are causal effects. Okay, and I'm interested in causal effects. So to start out with, suppose we have selection on observables. So the X's that I have are good enough to kill all the selection bias, meaning this causal model coincides with the OLS regression of Y on D and X, meaning I can estimate these coefficients by OLS. So I'm going to do that. I'm going to get theta hat for every school, and I'm going to get a standard error out of that regression. Instead of making things normal in finite sample, now I'm going to say, I'll just compute my robust standard error or whatever, and assume I have enough students per school that those standard errors are meaningful. Like they're a good estimate of the sampling variance of my theta hats. So I'm probably appealing to a central limit theorem. When I make this argument, theta hat is asymptotically normal centered at theta with a standard error that I can estimate well. Okay, so then we go to level 2. We have a mixing distribution for school value added. For now, let's keep that normal. Mu theta, sigma theta. And then we can apply the rest of our recipe. So step 2, I'm going to use my value added estimates for every school to estimate the parameters of the mixing distribution. And then step 3, I'm going to do linear shrinkage. Here's step 2. So this is a figure from the paper that I cited. These are bias corrected standard deviation estimates of school value added in Boston. So this is the excess variance in value added estimates across schools beyond what you'd expect from sampling error. We did 3 models here. One is the uncontrolled model, so there's no X's in there. That's obviously going to suffer from a lot of selection bias. There's tons of variation in school average test scores, which is what that's telling you. A lot of that is explained by the X's of the kids predetermined before they go there, things like their lag test scores and demographics. So these are the standard deviations correcting. For that, we did a control for past test score model and a first difference model. That's more like a fixed student fixed effect model, where we look at the change in scores. Those both tell us that there's standard deviation of value added across schools in student test score units. That's something like 0.2 sigma. Okay, so that would be my step 2. And then I'm going to go to step 3. So here are my unadjusted theta hats, a histogram of that across schools. In Boston, I've highlighted traditional Boston public schools within the district and charter schools separately. There are a bunch of papers using entrance lotteries to evaluate charter schools in Boston, finding positive effects. You can kind of see that in these value-added estimates. The charter sector is shifted over there. We're going to use that in a minute to make our model a little bit richer. But for now, this is just a histogram. So my mixing distribution model says there's a G underlying this of true effects. There's a distribution of true effects across these schools. If we assume that's normal, we can get a bias-corrected standard deviation estimate of the dispersion of that distribution. I've overlaid that on here. So in this case, my standard errors actually aren't that big. So that thing is only a little bit less variable than the unadjusted theta hats. The standard deviation of the theta hats is 0.22. The standard deviation of the prior is 0.197. And then I get my linear shrinkage estimates here. So this is the histogram of theta stars using this estimated mixing distribution, this deconvolved G as my prior, and that's what I end up with. Those are my minimum MSE estimates for each school in Boston. That's the distribution of those. You might notice that there's kind of a decreasing variance thing going on here. So the unadjusted histogram is more variable than the estimated prior, is more variable than the shrunk posteriors. That's, at least in simple cases, a theorem. It has to be the case. The shrunk estimates are by construction less variable than the prior distribution in order to minimize MSE. So that's actually worth dwelling on for a moment. The distribution of the theta stars does not tell you the distribution of the true thetas. And that's kind of a common confusion or error that you see in papers applying these methods. If you compute your shrunk posterior means and plot those, that doesn't tell you what the distribution of true effects looks like. That's not what it's designed to do. It's designed to give you estimates that perform well in an MSE sense, unit by unit. If you want to know what the distribution of true effects looks like, you're looking for the deconvolved G, not the shrunk posteriors. So each of these things is serving a different function. Okay. Any questions about that? All right, there's a few, yeah, Daniel.
Well, I guess it's related to the covariance in this example that had charters. So the way this is done is shrinking to everyone to the same average, right? But then if you were to estimate a model where you allow for different averages.
There you go. This next slide. So it's often natural to build in covariates. I kind of use this charter example because it's sort of obvious based on prior work that the charters are a bit different. Don't I want to use that? And the answer is, in general, yes. If I have a good predictor of theta, I can build that into my prior. So I could build a conditional prior distribution. If I want the simplest extension of what I was doing before, just make the mean, but not the variance, depend on charter status. So I could do my deconvolution separately for charter and non-charter, or I could, if I impose a constant variance, I just regress theta hat on a charter dummy, take the residual from that, deconvolve the residual, and use the charter coefficient as a shifter of my prior. So that's going to give me a shrinkage estimate that instead of shrinking towards a constant is shrinking towards a covariate-based linear index. That depends on whether you're a charter or not. That's what's going on in this picture. And you can see that generates posterior means that are a little bit more variable. There's more action in the posteriors because I have more information in there. And it works differently for charter and non-charter schools. So the charters that were near zero weren't moving before because the overall average is normalized to zero. This model thinks, well, are those schools really average? They came from a sector where everybody's pretty good. Probably my best guess is they're not, they're a little bit better than average. So I'm pulling them over here rather than there. Okay. Just a couple more points. I should give you guys a break soon, but a couple more extensions and variants of this linear shrinkage idea that come up a lot in empirical practice. So we talked about distributions of unadjusted estimates versus deconvolved prior versus shrinkage posterior means. That's one lesson to take from this. Another has to do with the use of these shrinkage estimates in a regression context. Yeah.
So you have these pictures now. So given these results, would you then be able to say that the charter schools are significantly better than the other schools?
So if you're asking me in a hypothesis testing sense, then I would put a standard error on this mu hat, and that would be my answer to that question. Because that's a feature of the true distribution of effects. Is the mean for the charter sector different than the mean for the other sector? That's a question about conditional G. Really, it's a question about, is the distribution G different for charter, the mean of that different for charter and non-charter? I would use my deconvolution estimate of G to answer that question. Here, that's just mu hat, which comes from a regression of theta on charter status. So you could just compute a conventional standard error for that. And do that if you wanted to do inference on that. In this case, actually, if I took the mean of the shrunk posteriors for charter and non-charter, that's actually going to coincide with the mu difference because the shrinkage is linear. In more elaborate non-normal shrinkage procedures, that doesn't have to be the case, that the means of the posteriors actually match the means of the prior distribution exactly. So the point is that if you're asking questions about the distribution of true parameters, you wanted to use the deconvolution estimates to answer those questions, not the shrinkage estimates. Okay. That's kind of related to this point, actually. Suppose I want to know how the true theta varies with charter status, say. And I want to do that in a regression context. So if I knew the thetas, I would just regress them on a charter dummy. And I want this parameter here, right? The OLS slope coefficient from a regression of theta on charter status. I don't know the true thetas. That's one of my main problems in life. So I have to do something else. I have to use either the noisy theta hat or the shrunk theta star. So which one should I use, actually, based on the logic that we just laid out? So I'm going to have to substitute something on the left-hand side of my regression. I'm going to run some estimate of theta on a charter dummy to decide whether the charter schools are better or not. Which one should I use?
It sounds like you've introduced some bias by shrinking, so you probably don't want to introduce that bias in your regression, so do the unshrunk. That's
correct. So the correct answer is I want to use the unshrunk because of the classic result that, you know, measurement error on the left-hand side of a regression doesn't screw you up. So it makes your standard errors bigger, but classical measurement error on the left is fine. Theta hat is an unbiased estimate, it has classical measurement error in it. And that doesn't bother me, so I can regress theta hat on charter status, and that tells me the right answer for average charter versus non-charter. If I shrink instead and put the shrunk thing on the left, I get the wrong answer, okay? Because I have non-classical measurement error on the left. The thing on the left is not an unbiased estimate of the y variable in the regression that I care about, and so I'm going to get something that's actually attenuated if I do that, because that's not the question that the shrunk posteriors are supposed to be answering. Now let's do the flip, which you can probably tell how this is going to come out. What if I wanted to know how some other variable w varies with theta? That is, instead of putting theta on the left and explaining it with charter status, I instead want to put it on the right and say, for example, do kids earn higher wages if they go to higher test score value-added schools? That type of question. So again, I don't know the true theta, so I have a choice. Should I regress something on theta hat, or should I regress it on the shrunk posterior? What do you guys think? Last time it was number 1, so it's number 2 this time. And it's for basically the same logic in reverse. On the right-hand side of a regression, classical measurement error is a problem. You get attenuation bias towards 0 if your regressor is mismeasured. So that's this here. I have a lambda times the coefficient that I want. If I shrink the regressor, I actually get the right answer, because the attenuation bias formula that you might remember from econometrics 1, the thing that's attenuating is exactly the signal to noise ratio in the regressor. And that's the thing that we're using to shrink. So that exactly fixes it and gives me back the correct regression coefficient. Okay, so this is a version of errors and variables regression. If you have a mismeasured regressor, but the variance of the error, and that you can fix the attenuation bias. This is like an empirical Bayes interpretation of errors and variables regression. So that's the rule of thumb for shrinkage with regression. You want to put unbiased estimates on the left and shrunk posteriors on the right, and not the reverse. Basically, because of these classic results on measurement error in a regression context. Okay, couple more points here before we stop. So we've been talking about MSE basically so far, and I told you via the James-Stein theorem, if you want estimates with improved MSE, linear shrinkage helps you with that on average across schools. Often we care about things that aren't MSE, so we have other objectives. So in the school value added context, I might care, instead of about getting a low MSE estimate, maybe I want to select schools that are in the lower tail of the distribution. So I'm an administrator or a policymaker. I want to find the schools with low value added, and my loss function looks like this. Okay, if I select a school, but it's actually a high value added school, I pay a cost of 1. So I picked one that actually didn't deserve to be sanctioned, or whatever I'm going to do with it. And if I miss a school that does belong in the lower tail, I pay a cost kappa. So this is like a type 1, type 2 loss function. If I miss, this delta is my decision. So delta is 1 if I pick this school. If I pick a school that doesn't deserve it, I pay a cost that's normalized to 1. If I don't pick a school that does deserve it, I pay a cost kappa. All right. And we can do the same kind of like risk type of calculations that we were doing for MSE for other loss functions like that. So formally, my risk of a decision rule, I'm going to pick a decision rule that says for each combination of theta hat and standard error that I might see, should I pick the school or not? That's the relevant decision in this context. What is the loss with this loss function generated by that decision rule? Well, we don't know the theta, so I can't calculate this directly. My risk is my expected loss, integrating over the distribution of thetas. That's this formula right here. It's just averaging this thing across the distribution of stuff that I do get to see. And you can probably already see that the optimal decision rule in a case like that is going to look like this. I should pick schools that have a sufficiently high posterior probability of belonging to that tail that I'm trying to find. So I pick a school, my optimal decision rule says, take theta hat and S and pick the schools that have a high enough probability of being below the cutoff C that defined my objective, and the cutoff that I have to, that I'm willing to, that I want to use to pick depends on my relative cost of type 1 and type 2 errors. So I pick based on the posterior probability that theta is below C, and I set a cutoff in that depends on these two relative costs. In other words, I'm selecting based on a quantile of the posterior rather than the mean. If I want low MSE, I use the mean. If I want to pick schools below C, I use a quantile. In the normal model we've been working with so far, that decision rule looks like this. It's kind of ugly, but it actually makes sense if you stare at it for a minute. So I pick schools that satisfy this condition. That's my decision rule. Something is below the cutoff. What's the something? Well, this part is just the posterior mean right here. Okay, so we've seen that before. And then I adjust that by this thing here that depends on the standard error for that school. So it's like I'm not ranking schools based on the posterior mean anymore. I'm ranking them based on the posterior mean and separately the standard error in a way that depends on how much do I care about type 1 versus type 2 error. So if I'm really upset about falsely penalizing good schools, then a school with a big standard error gets a reward in this decision rule, because it might actually be good, even if its posterior mean looks bad. And so I'm going to say, like, give them the benefit of the doubt. If I really care about missing the bad schools, then even a school that has a big posterior mean, if its estimate is pretty noisy, it might actually be bad, and I'm gonna pick it anyway. Okay, so this, and you can see this thing goes through 0 at kappa equals 1. So as I switch from caring more about type 1 versus type 2 error, that flips which way I want to use the standard error as a reward or a punishment in my decision. So I'm just showing you this to make the point that the functional of the posterior that you want to use depends on what you're trying to do when you report estimates school by school. Are you trying to get low MSE? Then you use the posterior mean. Are you trying to select schools with low value added? Then you want to do something more like this. And it's worth thinking about what is the decision actually when you're reporting the estimates. I think I'm going to skip a couple of these pieces and end on this connection to machine learning for the first part of the course. So, you know, what we've been talking about so far with EB is about essentially a bias variance trade-off type of idea. I'm willing to accept some bias in my estimates of the thetas in order to reduce their variance. And that sounds a lot like other things you might have heard of, in particular, the use of machine learning type models to regularize or penalize model complexity in order to reduce overfitting. Okay, so that's kind of the same idea. You know, what's machine learning? Lasso, ridge regression, random forest, pick your favorite, increasingly popular. And it's not an accident that those two things sound similar. In fact, they're the same, at least in simple examples. And I want to show you that in just a simple case, because I think the empirical Bayes view of machine learning is a useful way of deciding what ML procedure makes sense for what you're doing and figuring out, you know, what is the loss function I'm trying to actually minimize. Okay, so let me show you a simple version of this. Let's stick with, go back to the simplest possible example where I just have a school mean I'm trying to estimate. And let's make the mean of the prior actually 0. The mu theta is 0. So there's a dispersion of the means across the schools. The mean is known to be 0. And then I have everything normally distributed. So my unbiased estimator here is just the sample mean. I have these sample variances that are sigma squared over n. And let's make the n's the same also for all the schools. We already saw what the posterior distribution for theta looks like in this model. It's normal. Okay, and it has this linear shrinkage for its mean. The posterior variance is actually that thing that was in front of the by inverse 1 minus kappa in the last slide. It's this object right here. Okay, so my posterior is normal. But let's pretend for a second I didn't know it was normal. This is the general formula for my posterior density for theta. Okay, by the usual calculations, you know, it's the likelihood conditional on theta times the marginal for theta over the integrated version of that. So this is my posterior density for theta, given y. Because the posterior is going to turn out to be normal, I can equivalently think of theta star, the linear shrinkage estimate, as the maximizer of this density. Because for a normal distribution, the mode and the mean are the same. So another expression for the linear shrinkage estimates we've been working with theta stars is that they maximize this expression right here. Okay, so I can plug in the normal densities, take logs, because log is strictly increasing function, and my theta stars maximize this. It's like the log of the likelihood function plus the log of the prior density plus a constant that comes from this denominator that doesn't depend on theta. In general, we call this maximization of the prior of the posterior density the map estimate, maximum a posterior I. Okay, so I can also think of the theta stars as map estimates in this simple case where everything is normal. They look like this. Let me just do some calculations. Plug in the normal density. The log of the normal density is just going to involve some squares. Okay, squares coming from the likelihood function and the prior. I'm maximizing here. Let me multiply through by minus 2 sigma squared epsilon. That just leaves me with sum of squares in the first piece, plus sigma epsilon over sigma theta times the sum of square thetas in the second piece. Remember, this part was coming from the prior normal distribution. And I multiplied by a negative, so I went from a max to a min operator. And I can think of this object here. This is actually just a least squares problem, where I'm minimizing the sum of square deviations of y from my estimate of theta, plus a penalty term. So plus a constant times a penalty, and the penalty is a bunch of squared thetas. So what is that? That's ridge regression. Okay, ridge regression is just L2 normal, L2 penalized least squares, you do OLS modified by adding a penalty term that depends on the squares of the sizes of the coefficients. Okay, so linear shrinkage actually is ridge regression, where the penalty term, what's this lambda? Well, that actually has to do with the parameters of the prior. So the empirical and empirical Bayes is like you use the data to choose what penalty to apply. Okay, so it's like ridge regression with a particular data-driven penalty. All right, and the point of showing you that was that ML penalization type procedures, ridge is like the first ML procedure that you often learn in a ML basics class or textbook, or one of them anyway. They often have an EB interpretation, and you can think of the penalty that you're imposing as essentially determined by the prior. So here I got ridge because I had a bunch of squares because my log prior density was a normal. And that gave me the square penalty function. So ridge can be interpreted as the posterior mean from a model where my prior is normal, but you can see by the same argument, if I had made my prior Laplace distribution, meaning instead of the square that we have in a normal density, I have an absolute value operator, I would have gotten lasso out of that map estimator. So lasso is also interpretable as empirical Bayes, where your prior is Laplace or double exponential. It has that absolute value in the density function, and you're doing map. That is, you're taking the maximum of the posterior. Okay. So in my view, at least, when you're doing model selection or penalization with a machine learning procedure, it's useful to think about what is the implicit prior that's giving rise to the specific form of the penalty that's being imposed by that procedure. Lasso versus ridge, it's about normal versus Laplace, squared versus absolute value in the prior density, and the connection to the loss function. So should I be doing maximum a posteriori estimation, or should I care about some other functional of the posterior, in which case maybe this isn't what I want to do. Maybe I would want a different decision rule. So that's just kind of an advertisement for the idea that EB and machine learning are two sides of the same coin, and we can think through the logic of model penalization through the kind of EB decision framework. All right, I'm going to skip this too. Any questions about that? Yeah.
With ridge, we sometimes think that like we want to keep all the covariates, but we're just muting their contribution to the outcome. But these thetas are the theta j's that come from our like schools. So then, what's the analogous version of that? I'm keeping the treatment of kind of all the schools, but muting them. I can think of it.
You mean like the dense versus sparse type lasso versus ridge thing?
Ridge, I know how to interpret in like a machine learning context that I'm keeping covariates, but then here the theta j's, are these still the theta j's?
Yeah, these are the so what zero keeping means you're not setting it to zero, right? So what zero means in this context, zero was my normalization for the prior mean. So if I had a different prior mean, it actually would have been theta minus mu in those square terms in the ridge penalty. So what this means is if you keep a covariate, you don't shrink it all the way to the mean. So if I did lasso, I would be saying, actually, there's like a mass of schools that are very close to the average or something like that. My best guess, my maximum a posteriori estimate is going to put a bunch of them right at the mean, rather than just shrinking them close. And is that a good idea or not? Kind of depends on whether the distribution I've assumed is a good model for G or not. Yeah.
Is it fair to add on to that, like, when you first learn ridge, you have that regression context, there's the mean of the outcome, but in the regression context, those covariates are mean components, right? Like the betas. So when you shrink the betas to zero, overall, you're shrinking the outcome to like the MLE, right?
Yeah, so here your fitted value, you're thinking about like the fitted value that comes out of the y hat. So it is going to be, in this simple case, everybody attends one and only one school. So the y hat is the estimate for your school. So it's the linear shrinkage. It's like, what's my best guess of what your individual outcome is going to be? It's going to be the posterior mean data for your school. Does that make sense? All right. Yeah, I'm running out of time. So Let me just introduce this experiment that we're going to use for the empirical stuff in the rest of the talk, and I can give you guys a few minutes to mess around with the data from this in the break. So this is basically a experiment that I ran with some co-authors, Patrick Klein and Evan Rose, where we took a kind of EB view of the problem of trying to figure out which employers discriminate most or least on the basis of legally protected characteristics like race and gender. So we ran a large resume correspondence study. That's, as many of you probably know, an experiment where you send fake resumes to real job openings and randomize the characteristics on the resumes to manipulate employers' perceptions of who is applying. We followed the kind of work by Bertrand and Mullainathan and many other papers that built on their work by using race and sex distinctive names. So names that kind of evoke a race or sex assignment and use that to measure which employers are responding to those characteristics. Okay, so this experiment, we had 108 Fortune 500 companies in the sampling frame. We applied to 125 jobs per company, each in a separate county, and then we sent each job 8 applications. So each company gets basically 1,000 fake applications. Half of them are going to have a distinctively white name. Half of them are going to have a distinctively black name. Close to 100,000 fake apps total, although we didn't quite get there because some of the jobs, closed down and so on in the middle of it, but that was the goal. So this is just the sampling frame. And I should say, so the goal of this was to kind of study the heterogeneity across these 108 big companies in an empirical Bayes type framework to try to figure out how much variation is there in employers' propensities to discriminate on these dimensions. So these are like some of the fake resumes. Here is Joshua Erickson. Here's Maurice Randall. So distinctively white name, distinctively black name. We randomized everything else that's on the resumes independently of that. Jake was on the team that helped us do this. So he painfully aware of the stuff going on under the hood to generate these, but this is the end result. Here's some summary stats from the experiment. So we sent, in the end, 83,000 fake applications to 11,000 jobs at these 108 companies. And these are the overall differences that we found in the experiment. So the overall white-black difference in callback rates was 2 percentage points on a base of 25%. So for white names, we got a 25% callback rate. Distinctively black names got 23%. The t-stat on that is 12. So it's a it's a modest effect, but it's very precisely estimated. Of course, it was so powered up for the mean because that's not what we were interested in. We're interested in the variation. So we did our power calculations for the variance, the bias corrected variance estimate instead of the mean. Okay, here's gender. So gender was a very precise 0 actually on average across all the companies in the experiment. Male and female names got the same callback rate of around 24%. But it's going to turn out that actually there's a ton of spread across those 108 companies in both of these gaps. And that's basically what we're going to spend the rest of this time studying. Let me pause here and let you guys play around with the data a little bit while we take a 20-minute break or so before the next session. I posted it. I don't know if we have a website for this class. I also put it on my own website this morning. So if you
received it yesterday and today.
Okay, so you guys have it. There's like a lab assignment in there, and then there's a data set, and hopefully it'll be of interest to you guys. We recently released the names of the companies in this experiment, and I put them in the data set that I uploaded for this class. So you can see which companies are in the tails of this distribution and try to decide using your empirical Bayes posteriors who's discriminating and who's not. So I'll give you a few minutes to do that, and then we'll come back and show some results on the slides. Maybe in 20 minutes. 20.
Okay.
Yeah, let's do 20.
Or not. It's like after. Yeah, I guess. I think, but yeah, your example is closer to learning and it's where each of the stations is a human being.
Should they?
They're the average.
I'm doing this and we learn at
Yes.
But I guess it's close, but there's only minus that it's
Yeah.
not.
That's right, so that's gonna. That's basically just. I've been assuming that's square.
Like
Yeah, Brian.
Yeah, and I think that. Like, maybe well, it says something about how we're just described.
every remark is pretty similar.
But across what's to solve it, that's what I. So they can like. 5 by X, you have your estimated.
Cookies also go very not.
Or across the way.
Sorry. Can I get the email for you too? Should I send it to you? Not type it.
We don't spend.
That's it, my vision group, like, really
First, then, I guess. Yeah, actually.
Same aspect. So the called forest is like high dimensional
Right.
covariance. So conceptually, it's predictable enough. This conditional algorithm. It is going to give you a person, and it'll probably be different for each person.
Right.
But that's like, it's like an estimate of the conditional. So that's like what you're studying here. Variation. Treatment of measurement.
So, yes.
Yeah, so that's what I want.
It's related, but repeating. I showed that thing. So in that case, we can go and I.
Yeah.
If you work with them, know how much.
Well, okay, so what do we
More
want?
fun projects?
Do you want to answer?
Yeah.
So I don't know if they're causal for. I said really. You want that sentence.
Come up with a custom decision loss.
Do that.
How many number of MDs do
Sounds like.
we?
I
Get
know.
visits for use of cells.
Sounds like they have.
We stopped the use of the baseball.
So you simple.
Yeah. Rightly so.
So we're also. And then if you want to use that. Mostly for like.
That part was similar to
That kind of question.
That prediction there is not gonna.
Remember, my memory is easy.
While I know that discretion.
And we first met. Thank you.
Yeah, so I want to read that.
SQL was there. This guy.
So you have classical, but if somebody really wants to get. Your data is spread.
SQL will never go away.
And also, probably.
It's too useful to go away.
No, right now. And then I do have a problem that I do have. No, I mean.
Last thing I think, when we think about it.
That's fine, trying to.
So then they come back and then.
Well, so what they, no, what they did is, so they had the mainframe. They got, wow, I mean, COBOL runs to be flat. So that complexity. So I don't know.
Let's say that I.
More people than people.
How this varies by.
That learned in the past.
Yeah, I mean, here, but it's here.
Yeah.
I mean, our data's all- yeah. They have different standards. Yeah, they use
It's not like what you
Like the meteorology. No, like compared to like working with C++, like it's all right there. Everything top to bottom. Nothing's really going on. You know, sign is always an addition. Here's kind of like the economic software. And then don't be back until it's been running however long. And like these things, like after the first 10 years. It's about to check out your cost. 100%. It's all bad. It's like, what's the one for one step? Yes, that.
And that's according to what you said.
Same way.
Seems like you have that. Warning a while ago. That's right, but I wouldn't even, I don't think you.
Well, I think that's a question. Already after training. 3 years. Like my job is a gen ed. Like, yeah, I thought. So, yeah.
You be in charge of science.
Yes.
I feel like every time I coordinate, we all.
No, you still. Some base. Just like.
There's small.
Literacy and.
Just like
adding a person.
And then I think what's like,
It's interesting. The data science. Those data. I mean, every time I read song, it's like stylistically correct, that's all the bad.
That's the same, that's the equivalent. I wouldn't use any. Question that.
No, but we can.
So I could say, what share of those?
You got
I think I have like 4 of these different 2 steps. Is SSE, SSE duo.
Let me work through it.
I was gonna say kinds of things so bad right now. I finally got. Log into the server. Still don't have. Not so. Can you check? Pull that shit.
It's still better to not have that. Limit. Right. Yeah. But you can see that tells you how much.
Yeah, let's talk about it. Yeah. Login. Like the bonus selection is.
The more, the closer to now. The more.
Oh, yeah. You know, but
Still better.
there's a while.
I have 1 over 3 times. It's 6 times to the person.
It's a very specific sort of question. I need your. In the sense of like.
They might still go by that.
Yeah, normally it's kind of a dog.
All in our place, basically. Now, when you get a notification.
That's all like step two.
Regular.
The shrinkage thing is about supporting something that does well. An average possible. Or like a different problem that you say.
That's it.
Care about it. You could say it, you're trying to do the inference problem. Repeated. That's the most. That's like, I want to. I'm gonna. I want to. That's like, that's false discovery. Conditional on me. That's all problem. That's the professional type of error. You know, would I? If I could lose that. That is the question about doing it many times. So the type one error.
Yeah,
Dealing with population. 100%. This is about control. Making sure that state they mostly do, or they mix it all. And then I can decide.
You really want that.
And then my decision will go through. Of course, again, it just threw me off. I would switch my decision. I wanted to solve. That's why I should. That was kind of abstract.
Four other jobs. Say 20 seconds, depending on how much you can decide, but it's really that 20 seconds.
I just want kids.
Starting stage.
Fine.
It's gonna get to
yeah, I know. And I thought about
Okay, I'm gonna start up again in a minute, because I don't want to keep you guys over time. So we're going till 4, right? 4, okay. So hopefully, for those of you who are interested, you got a chance to look at the data. I'm going to show you results from that same data as we go, which will mostly answer that problem set or lab or whatever you want to call it. The solution program is also in that same folder, but we'll get through it. So, you know, this experiment is going to be like a working example as we go. I'm going to show a bunch of results from this, but to start with some more abstract discussion, the first part of this was basically a lot of semi-toy models with normal distributions, independence assumptions, just to illustrate how these things work. And we've seen that actually sometimes that's not bad, because even when we use models like that, we can get procedures that generate improvements under much more general conditions, like as we saw in the James-Stein theorem. But we're next going to consider some extensions of these ideas that relax those assumptions and think about this as a more robust or non-parametric empirical Bayes type setup. Okay, so this is like, how do I estimate the variance across parameters in a more general case, or parameters across units? How do I do deconvolution if I care about other features of G beyond the mean and variance, and I want to be flexible about that, issues of precision dependence, non-parametric shrinkage, and so on. So generalized variance estimation, a lot of the questions that you all asked early on were actually kind of about this. So let's, again, dispense with the random effects view and say we're interested in this set of parameters, theta 1 through theta j. Okay, and I'm going to make those a vector now, big theta, just collecting all the parameters for each group. I have an estimate of that. I'm theta hat. Okay, so that could be a list of sample means or something more complicated. And I'm going to assume that's unbiased, like before. So E of theta hat given theta is theta. And then there's noise in those estimates. And that noise is now described by a big matrix B, which is E of theta hat minus theta, theta hat minus theta prime. So, in the simple case we had before, B was diagonal. There's just a bunch of S squareds along the diagonal. Now it could be anything. There could be covariances between different estimates. Maybe they came from the same sample. Maybe they're two estimates for the same outcome or something like that. Just any V. Okay. And we're going to think about trying to learn about parameters that look like variances. So let's suppose we have a parameter of interest that looks like this. I'm going to call it delta. It's some quadratic form in theta. So it's kind of abstract. Theta prime A theta for some matrix A that I choose. To make this concrete, I could choose A equal to this. So identity minus this outer product of ones scaled by some 1 over j's. If I do that and we work through the math here, that becomes the variance of thetas essentially across the groups. So it's sum of theta j minus theta bar squared averaged over the theta. So I can think about that variance of parameters across the finite sample of units that I'm dealing with as a quadratic function of theta. And I'd like to estimate that. A simple thing that I could do is the plug-in estimator, which just puts a hat on theta. So stick your unbiased theta hats in there. That's like taking the sample variance of theta hats. So the total variance of school means. That estimator is biased for the same reason that we discussed before. This is a nonlinear function. Okay, so even though theta itself is unbiased, the nonlinearity of the quadratic form is going to screw you up. And this is due to the intuition that theta hat squared is an upward biased estimate of theta squared because theta hat has noise in it. So you're kind of squaring the noise, and that's not disappearing. All right, so this plug-in estimator is biased. You can work out exactly what the bias is actually with some trace tricks, which I did here. I'm not going to go through the proof, but it basically says that this generalized variance estimator, this quadratic form in theta is equal to the true quadratic form, the actual variance of the underlying parameters, plus this thing, which is the trace of something to do with this V matrix hit with whatever weighting function that I chose. Okay, so because I can work that out, I can actually fix that as long as I have an estimate of V. Okay, so suppose I have an estimate V hat available and I just stick that in, I just subtract off that bias component. So this is just like in the simple deconvolution case we had, subtracting off the average squared standard error to try to get rid of the noise. This is doing that for any general quadratic form that we're trying to fix. The problem, I'm going to call this delta hat bias corrected because I took out this trace AV. And if the V hat that I have there, so as Daniel asked earlier, maybe my standard errors are not literally the sampling variances of the estimates. Those are themselves estimates from the data. Then some of them might be wrong, and they might be off. They have a sampling distribution of their own. So that's the distinction between V hat and V. But if I have an unbiased estimate of V, such that E of V hat equals V, then this object here is an unbiased estimate of the quadratic form of interest because trace is also a linear operator. Okay? So what this says is that for any general quadratic form, as long as you can form unbiased estimates of your squared standard errors, and any covariances that belong on the off-diagonal pieces of that matrix, you can do bias-corrected variance estimation. Okay, and this paper by Klein, Saggio, and Salston has a leave-out method for getting an exact finite sample unbiased V hat. So you can do exact finite sample unbiased variance estimation for general quadratic forms. As we discussed earlier, actually, you pay a price for promising to be exactly unbiased in finite samples. This thing can be noisy and it could be negative easily, even though the quadratic form can't be negative, because even if the true variance is 0, this thing wants to be unbiased. So it's promising to be unbiased for any A and any theta. And so it seems kind of crazy to report a negative variance estimate. Maybe you want to fix that by using a less noisy V or taking max of this as 0, then you're accepting some bias. But you have, probably better variance properties of that type of estimate. Okay, this is just to say we can do a much more general version of that subtract off the average square of standard error thing to figure out what is the dispersion in parameters across the units we're dealing with, or what are other variance and covariance type parameters of those units. So this is a fixed effects view. Here I'm treating the thetas as fixed and getting interested in a quadratic form in those fixed thetas. But if I go back to the empirical Bayes type random effects view, by iterated expectations, if this quadratic form that I'm interested in is an unbiased estimate of the mixing distribution, then the bias corrected estimate of that is also going to be an unbiased estimate of the variance of G. So, if G is my mixing distribution, I'm drawing a finite set of thetas sampled from that. If I put it like a J-1 here, that would be my sample variance of the thetas. And so with that A, this is going to be an unbiased estimate of the variance of G also by iterated expectations. Okay. So this is what we get if we do that in this discrimination experiment. I showed you the means already, right? The mean effect of a distinctively white name was +2 percentage points. The mean effect of a distinctively male name was essentially 0. These are the square roots of the unbiased variance estimates. So for race, it's 0.19, about the same magnitude as the mean effect. That means if you move up one standard deviation in the distribution of discrimination, you're kind of doubling the mean. So we at least interpreted that as a lot of heterogeneity. For gender, it's even bigger. It's 2.7 percentage points, despite the fact that the mean is 0. So what is that about? How could that possibly be true? That must mean that there's some going in both directions. And we'll see that in more clearly in a few slides. But that sort of highlights why these distributional questions can be interesting. If you're doing an old school, treatment minus control RCT evaluation of this, you'd report this and say there's nothing going on with gender. Actually, there's a ton going on with gender. There's even more heterogeneity there than for race. It's just in the second moment and not the first moment. So here's like our plots analogous to what I showed you for schools. Now for the discrimination example, this is a histogram of white-black name contact gaps across the 108 companies in this experiment. So our standard deviation of the estimates was 0.26. Unbiased standard dev was 0.19. That's subtracting out the component that's due to sampling variance. I think this was on the lab, so some of you may have made this plot. Here's what the linear shrinkage posteriors look like. So there's quite a bit of shrinkage going on here because you can see by the difference between the unadjusted standard deviation and the bias corrected standard deviation. That's a much bigger difference than what we had for the schools. There's quite a bit of noise in some of these estimates. So you shrink a lot towards the mean. The standard deviation of the posteriors is 0.13. So this is another illustration of the fact that the unadjusted are more variable than the true mixing distribution is more variable than the shrunk posterior means that you choose to minimize MSE. Okay. So that's what you would do if you care just about the mean and the variance. This is an unbiased estimate of, the square of this is an unbiased estimate of the variance of the mixing distribution, regardless of its shape. I didn't assume anything in these calculations about what G is. I just am looking to get the variance, but maybe I want to know more than that. So I want to know more I want to answer some more sophisticated or nuanced questions about the mixing distribution. How would I do that without just assuming it's normal and kind of assuming all that away? Okay, well, that's non-parametric deconvolution. So this is the idea is to flexibly extract the distribution of heterogeneity across units using the noisy estimates that we have under minimal assumptions on the shape of G. So I'm going to show you a couple ways to do that. An important note here is that for this purpose, to kind of go to the higher moments, we do have to take a stand on dependence between the effect sizes theta and the standard errors S. So I'm going to build a likelihood function for theta hat that conditions on S throughout. So if I don't allow S to affect the mixing distribution, I'm imposing an independence restriction, which could be false. And we'll come back to that, but let me just impose that for now and show you how these non-parametric things work. There's kind of two versions of this that that I want to show you. The first is like the classic non-parametric maximum likelihood estimator, NPMLE it's called. This has a very long history actually going back to these papers by Robbins and Kiefer and Wolfowitz in the 50s and so on. Economists are often familiar with this from Heckman and Singer, which were doing like flexible hazard models essentially with unobserved heterogeneity. But NPMLE, the idea is to say, well, there's a distribution G that I want to estimate. Okay, what I get to see are the theta hats. I know those are, I'm going to treat those as normally distributed based on the asymptotic argument for each unit. I know their variance, it's S squared. If I want to estimate a distribution, then why don't I just write down the likelihood function and maximize that? So this says pick G hat to maximize over all distributions G, this likelihood function. This is the integrated likelihood where this is the likelihood conditional on theta, and I just integrate that over theta. Okay, so the solution to this problem, it looks formidable because I'm maximizing over a wide space of distribution functions. It's known to be a discrete distribution with at most J mass points, where J is the number of observations in my sample, and it's actually not that hard to compute with modern optimization methods. Conker and Mizera have an efficient approximation to the likelihood function that works well, and you can implement this in R yourself with this RE Bayes package. So if you want to do NPMLE, just take that off the shelf and do it. One disadvantage of this is it produces this discrete distribution. So you're going to get mass points in there. For a lot of purposes, that's sometimes unattractive. Do we really think that there's like discrete masses of firms that discriminate by certain amounts, or do we want to think of it as a continuous distribution? One modification on this that I like is this log spline deconvolution estimator from Efron, which is basically approximating G with a flexible exponential family distribution, but smooth, and parameterizing the density function with a natural spline. Okay, so this is the math on how that works. This is just some fancy notation to say we're going to have a vector of spline coefficients alpha that determines the mass at each, or the density at each point. And then we basically solve that same NPMLE problem, restricting our search to distributions in that family with that smooth spline structure. And then Efron proposes to penalize that likelihood function with something that looks like this. We have a penalty term times square root of a quadratic in the spline coefficients. So going back to our logic from earlier, this is like imposing a little bit of like a hyperprior on G to say, I'm going to smooth this a little bit because it's going to be noisy. It's a very flexible model. This pushes G hat towards a uniform distribution, actually, because that would want to make these alphas all the same. With this parameterization, that's going to put the same density at every point. So it's like you kind of push it a little bit towards the uniform to smooth, but otherwise you're essentially just maximizing this parametric likelihood function. Okay.
So can you do cross-validation to choose the C or something like that?
Yeah, you could do it that way. The way that we did it in the stuff I'm going to show you is to choose this so that the resulting distribution matches the bias corrected variance estimate. So that's kind of like a moment-based validation procedure to say, like, there's stuff that we understand and are comfortable with about our ability to estimate the heterogeneity distribution. The mean and the variance should be right if it's working properly. So we're choosing the tuning parameters to match those, but there's other approaches.
Is there any result that like it provides a unique C to do?
Not that I know of. We did it with a brute force grid search, at least when we started doing this. So yeah, I don't have a result on that for you. So this is what happens when you do this for the discrimination experiment. So the color of this changed because I went from Stata to R to implement this, but it's the same histogram. This is the log spline deconvolved density. one interesting thing about these racial gaps is that there's actually very little mass below zero. Not many companies were estimated to discriminate kind of in reverse against distinctively white names. And actually, if you do a test that's all sampling error using a moment inequality type procedure, the p-value on that is 1. So the data really likes the idea that discrimination in this environment is only going one direction. Everyone is discriminating against distinctively Black names, just some more than others. So the nice thing about these non-parametric type procedures is you can impose shape constraints like that pretty easily on those likelihood functions. This is what happens when we do that. This actually did a better job of matching the mean than the one from the previous slide. So we calibrated this to match the variance estimated, the estimate, as I just said. So both of these match that, but the mean fits that 2.1 percentage points that we saw before when you impose the shape constraint that it's all going one direction. So this looks a bit like a log normal distribution rather than a normal. Okay, here's the NPMLE. So it's spiky, it's a discrete distribution. It kind of has similar moments, but I like the smooth one for what it's worth. I don't know what I just did.
So clarification.
Yeah.
So in that, you're essentially saying that all the negatives you observe are just due to sampling.
Yeah, and we test that, we can't reject that. Of course, that doesn't mean it's true, but it seemed to be a good approximation. I don't-
Control L on the keyboard.
I don't have a keyboard or a mouse. Oh, there's one over here. Okay. Magic. Okay. Control L. There we go. Okay. So let me show you gender also. I didn't put that in the data set that I uploaded, but this is kind of interesting. So this is the histogram of gender contact gaps, male minus female across firms. These look a bit different than the racial gaps. You could see it's kind of symmetric about 0. That's consistent with the fact that the mean is exactly 0. If you do the log spline deconvolution on this, it looks very different than the distribution for race. It looks more like a Laplace. It's very peaked at 0, but it's got these tails sitting out here. And you know, as we saw before, the mean is basically 0. There's a big standard deviation of that. So the NPM, the log spline thing is basically recovering that. Here's the NPMLE. For gender, it's also a similar character. You know, there's these firms that are sitting way out here in the tail that are, you know, this one, for instance, is favoring women by like 20 percentage points. And the NPMLE says there's a standard error on that, but I think that's real. So it's putting a little bit of mass out there to find that one. Yeah.
How much better is this than the normal we talked about earlier?
How much better?
Like, especially in this case where it's symmetric.
Yeah, I don't have a perfect answer for you. Better in what sense? I mean, you could ask
No,
if I force this to be a normal, what's the degradation of my likelihood function? It has to be, this is the maximizer, so it has to be a little bit worse. How much worse? I don't know, actually. Some features of it that we were interested in do look different than the normal, as I'll show you in a second. But yeah, I don't know if we could really reject that this is exactly normal. It does look more peaked, but that's just a visual interpretation. So here's, you know, one interesting thing you can do with these types of non-parametric estimates is you can answer like richer questions about the distribution that would be trivial or just functions of the mean and variance. If it were a normal, this is like the Lorenz curve. So the idea here was to say, let's array the firms by how much they discriminate. For race, it's discrimination against distinctively Black names. For gender, it's actually the absolute value of the gap because we know they're going in both directions. And then we say how much of the total discrimination, meaning the total missing callbacks that would have occurred if all the firms were not discriminating, how much of that is explained by firms at each up to each percentile. So it's like what you're used to seeing for an income distribution, but for a discrimination distribution instead. And then the Gini coefficient is giving you the discrepancy between the perfect equality curve and the estimated Lorenz curve. These are coming from the log spline G hats. So we have G, and then once you have G, you can estimate anything you want about that. So what we see here is, for example, the top 20% of discriminating firms are estimated to account for 46% of the discrimination against distinctively Black names in the experiment. For gender, it's 56% of the missing contacts as a result of gender discrimination. The Gini coefficients here are roughly comparable to US and Brazil level income inequality. So it's, at least by that metric, quite a bit of dispersion, quite a bit of action in the tails. All right, so that's, and I guess just to reiterate the point I said earlier, like these come from the deconvolution step. These are questions about distributions. If I took the shrinkage estimates and computed the Lorenz curve for the shrinkage estimates, it's not going to give me the right answer because it's solving a different problem. This is my best estimate of what the underlying heterogeneity distribution looks like, which is what we should be after, if that's the kind of question we're asking. All right. I lost my clicker, it looks like. So let me come back to this issue of precision dependence, which has come up a few different times. So I've been imposing throughout, including in those non-parametric formulas I showed you a couple of slides ago, that the effect sizes theta j are independent of the sampling variances sj squared. So what does that mean exactly? Like what do I mean when I say that, and why is that a restriction? Well, to get the intuition, it's useful to go back to the simplest first example where all we're doing is estimating a bunch of means. And remember, the squared standard error for a sample mean is just sigma squared over n. So if I estimate that separately by group, sigma squared could be different, n could be different for each group. And it could be that the effects theta are related to those two things, one or both of them in one way or another. So maybe units with larger sample sizes, n, have bigger or smaller effects. Maybe units with more variable outcomes, sigma squared, have bigger or smaller effects. So in the discrimination experiment, at least for n, we tried to make that a non-issue by balancing n across the companies. We tried to send the same number of apps, but that's not always the case. One area where this comes up a lot is actually meta-analysis, where empirical Bayes tools get used a lot to understand the variation in effect sizes reported in the literature, say. And you might think that researchers have some sense of the effect that they're expecting in their context, and they sort of choose n with an eye towards how much sample do they need to detect that effect. So it might be, and if that were true, you would have smaller samples in settings with bigger effects because you do your power calculation and you're thinking, well, this is a big effect. I don't really need to gather that much data to find this. And so theta will be correlated with n, if that's true. It could also be true that the underlying kind of structural variance of the outcome in different cases is related to the effect size in some way. So that's actually substantively interesting. I guess one more example that I like, teacher value added is a one literature where we see a lot of empirical Bayes tools being used. And a stylized fact in that literature is that teachers get better with experience. So theta is higher the more data you have on someone because they're more experienced, and so their theta is improving. So the new teachers tend to have lower thetas and smaller and bigger standard errors. Okay, so you sort of have to deal with that. So if you're worried about a problem like this, in principle, you need to condition the mixing distribution on S to build the likelihood function. To get the mean and variance, you actually don't need that, right? The bias corrected variance thing I showed you, I didn't make any assumptions about that, but for these likelihood-based deconvolution procedures, you sort of do need that. So how would we do that? There's a few different ways to handle this problem. One is just to kind of specify a model to fix this. So maybe I think that the effect size is related to the standard error, and I'm willing to write down some model for that relationship. So maybe theta is linear in log S or something like that. And I'm willing to treat the residual from that as independent of S. So there's just dependence through the mean. If that were true, then we're back to the case that we had earlier where S is just serving as a covariant that shifts the mixing distribution G. Okay, so I can do it that way. There's generalizations of that simple procedure. Kevin Chen, who was on the job market this year, had a recent paper where he proposed an interesting kind of location scale model of dependence between theta and S to sort of fix this, and then worked out the NPMLE type procedure in that scenario. So that's one thing you can do. A simple alternative to that is just to kind of stratify the sample by standard errors and estimate different mixing distributions by bin of S. So that's what we did in this case, you do this, you get kind of lumpy mixing distributions because you have different underlying distributions for different S, but the marginal looks, roughly the same as what we had before. I'm going to skip this. A traditional solution to this problem in statistics is a variance stabilizing transform. So in certain cases, you actually kind of know how the mean and the variance should be related. For a binomial distribution, for example, if the success probability is P, the variance of the Bernoulli trials is P times 1 minus P. So you sort of know how those two things are linked, and you can do a transformation that gets rid of that variance dependence. For the binomial, it's the arcsine square root transform, which is kind of the classic one for fixing this, but these aren't generally available for all distributions. So there's kind of a limited subset of applications where you can do this. Okay, so non-parametric shrinkage. So now let's suppose we've picked our favorite non-parametric estimator for G. We've handled any precision dependence that was present. We have for G hat. So now what I can do to generalize the basic linear shrinkage James Stein type procedures we saw before is to use my non-parametric G hat as my prior and form posteriors based on that rather than a normal distribution. So this expression here is what my posterior density is going to look like. And my new non-parametric posterior mean, theta star, integrates over that density to get my minimum MSE prediction of each theta, assuming that my model for G is correct, kind of doing the plug-in estimator, which will generally differ from the simple linear shrinkage estimates that we saw before. So again, we're kind of in a world of robustness, efficiency type trade-off, potentially in this scenario. So if in fact G is not normal, it has interesting action in the higher moments, and I've estimated those accurately with non-parametric deconvolution, in general, the nonlinear shrinkage is going to work better and give me a richer picture of the posterior mean. On the other hand, to get the linear shrinkage estimate, I only needed the mean and variance, which I can get under minimal assumptions. So I could just do this and rely on the basic approximation results, which say the OLS fitted value is going to be pretty good, even if the data generating process is not exactly normal. And that can actually do better than the non-parametric posterior if G hat is noisy. So you sort of need a lot of data to do non-parametric deconvolution. It might not always work that well. But in any case, here's what the non-parametric deconvolution estimates look like for the discrimination experiment. So here, the red bars are the unadjusted white versus black contact gaps. The blue curve is the deconvolved density imposing that shape constraint that it doesn't go below 0. And the blue histogram is the set of posterior means generated by that non-parametric prior. So one attractive feature of this nonlinear shrinkage procedure is it kind of inherits the right properties of the prior distribution. So we at least thought that it's credible to impose this shape constraint that this is all noise, and there's actually only discrimination against distinctively black names, no discrimination against white names in this experiment. The posteriors, because they were based on a prior with that property, also have that property, right? There's no mass below 0, whereas the linear shrinkage estimate, some of these would be over here. So that's what our posteriors look like. Here's what it looks like for gender. Again, it's kind of mimicking the structure of the prior distribution, but shrunk down roughly towards the mean. You can see that, again, this estimate is pretty precise. So the non-parametric shrinkage procedure finds that and says that one basically real. There's minimal shrinkage going on with that. That firm is discriminating against distinctively male names dramatically.
Chris, is that Victoria's Secret? You didn't share
That one is not, I guess I'm allowed to say this. I've presented this paper so many times before we released the names that I'm not used to saying them out loud. I think this one is Ann Taylor. If I remember correctly. Yeah, Victoria's Secret is also negative, but I don't think quite as negative actually. Yeah, I'll just leave it at that. Okay, so the last set of things I was going to do in this lecture is to talk about some multiple testing type applications of these empirical Bayes procedures, which is, it's natural to transition to this from the non-parametric EB, because this is a place where we kind of have this robust EB interpretation where we're trying to make minimal assumptions about what's going on in the underlying mixing distribution, and we want to make decisions that perform well under those minimal assumptions. So this is where the title, the second half of the title for the workshop came from. Efron calls this large scale inference. The idea is you have many hypotheses you're kind of simultaneously interested in, and you want to adopt a decision rule that does a good job of selecting the right ones on average across those many decisions that you have to make. So it's very similar to the kind of average MSE ideas we were talking about in the simpler examples earlier, but here it's about testing and selection rather than minimizing MSE. A lot of these ideas came out of like biostatistics and medicine type applications where people are trying to figure out, you know, what genes are responsible for some rare disease, and you have 10 million hypotheses you need to test, and you have to figure out which ones are real. So that's kind of where some of this language comes from, but we're applying it here in social science. So to formalize this, let's suppose we're interested in some null hypothesis involving the theta parameter for each unit, maybe theta equals 0. So this could be which subgroups are affected by some intervention. You know, if J is indexing covariate bins in a randomized trial or something, you could say which effects are actually real, which groups are benefiting. In the experiment that we've been working with, which firms are discriminating against applications with distinctively Black names, which ones maybe are not. Okay, and let's let T be an indicator that's equal to 1 if that null is true for unit J. So it's a truth indicator. Of course, we're not going to ever see that for sure. And then let R be our decision, basically, which is an indicator equal to 1 if we reject the null. So if we decide the null is false, so this effect is real for this one. So this is kind of basic multiple testing, but our traditional hypothesis tests are about controlling type 1 error size for a single test. That is limiting the probability of a false rejection, assuming the null is true. In other words, I'm adopting a rejection rule that has this property. Probability that I select reject, conditional on null true, is below some limit, alpha. So that's type 1 error control. If we're simultaneously interested in doing well across many hypotheses in one of these large-scale inference or multiple testing problems, it's actually not totally clear what notion of aggregate error we should control. There's different proposals for this in the multiple testing literature. You can control the family-wise error rate, which you could think of as the probability of at least one mistaken rejection. So I think about what's the probability I make one or more mistakes with my decision rule. I'm going to limit that probability across all the tests that I'm doing. That is usually very stringent if the number of tests is getting really, really large. If I only allow myself one mistake, probably I can't do very much. An alternative, which has received a lot of emphasis in this EB style testing literature, is about false discovery rate control. So the false discovery rate is the expected share of rejections that are mistaken in repeated applications of your decision rule. That is, among those you selected, among the genes you say are responsible for this disease, or among the firms that you label as discriminating, how many of those are incorrect? Okay, so that's different than type 1 error control because it's flipping the condition, right? Instead of saying conditional on the null being true, let me limit the probability that I reject. It's saying among those I reject, how many are true? And I want that to be small. That's the false discovery rate. Okay, so for large scale testing problems, family-wide error control can be stringent. I'm going to focus on FDR for today to give you a flavor of how this works. Okay, so to do this, let's suppose we do a test for every unit and we get p-values p1 through pj. And we're going to consider a class of decision rules that reject all hypotheses that have p-values below some threshold, p bar. How many mistakes do I expect to make if I do that? Well, I can use Bayes' rule to help me think through that. Okay, so my decision rule is reject if Pj is less than P bar. So among those that I rejected, how many are mistakes? Well, that's the share of nulls that are true among those that are rejected. And by Bayes' rule, that's the probability of reject given true times probability of true over the marginal probability of reject. Okay, so that object, it's often written differently in literature, but that object is the false discovery rate for our decision rule in this framework. It's the share of rejected hypotheses, so conditional on reject, that are actually true. That's my false discovery rate. And if I can limit FDR, the nice thing about FDR control is I can be reasonably confident that the rejected hypotheses are false. If I know only 5% of the ones that I reject are true, then I'm pretty sure about the list that I have at the end of the day. The firms that I label as discriminating, I'm pretty sure about that. If I have FDR control, I can't be sure in that same sense if I'm doing type 1 error control test by test. Okay, so let's scrutinize that expression for FDR and think about what we can learn about it. Okay, so was there a question?
It's about the expression, so you can go ahead.
Okay, so this is FDR. I'm writing it as FDR P bar because P bar is like my decision here. Essentially, it's the threshold limit for the P value that I'm going to select for rejection. So my FDR expression, it's the marginal probability of reject given true. That's the thing that we're used to from conventional hypothesis testing. P values should be uniformly distributed under the null, so that's just P bar. Okay. The other piece in here is the probability that the null is true, the marginal probability that T equals 1. I'm going to call that pi naught. Okay, and then the bottom is the marginal probability of rejecting, which is the share below P bar, the share of P values below P bar. That thing in the denominator, so P bar is something I pick. The thing in the denominator is not hard to estimate. I can just look at my data and say, well, what share of nulls are below P bar? I can estimate, I can put a hat on that. The thing that I don't know that really determines how I should interpret all my test results is pi naught, which is like, what is the population that I'm dealing with? In particular, it's the share of true nulls in that population. So if most of the nulls are true, it's hard to find the real effects, right? In fact, if pi naught equals 1, all rejected hypotheses are actually mistakes. They have to be, because there's no real effects out there. On the other hand, if pi naught is equal to 0, all rejected hypotheses are false, but so are all hypotheses I didn't reject, and I should have actually rejected everything because none of the nulls were true. So pi naught is kind of what I need to know to decide how aggressive I want to be in rejecting tests. And in the empirical Bayes worldview, we kind of recognize that pi naught is a feature of G. Actually, it's a feature of the distribution of parameters in the population that I'm dealing with in my repeated tests. So I can write it like this. It's an integral over the region of G where theta is equal to 0, if theta equals 0 is the thing that I'm interested in testing. So because that's a feature of G, our question is, can we use empirical Bayes methods of the type that we're hopefully getting used to throughout this workshop to get some traction on pi naught and use the data to kind of figure out a rule that controls FDR in a desirable way. So a conservative approach that you could take, the maximally conservative approach, is just to plug in pi naught equals 1, that expression. Right? It's a probability, it can't be bigger than 1. So that was kind of the original proposal for FDR control in this literature. And that's actually, it doesn't result in a totally trivial problem because it's still possible that for a given P bar, you have many P values that are close to 0, way more than P bar actually. So if a huge number of your P values are essentially 0, then the CDF evaluated at P bar is going to be much bigger than P bar because the P value distribution is very far from a uniform. Okay, so you could still develop a procedure for selecting P bar to control FDR and reject some hypotheses, even under that maximally conservative approach to plugging in pi naught equals 1. But it's kind of obvious if you think about it that we can do better than that. it's logically inconsistent to have pi naught equal 1 if we see that the distribution of p-values is extremely far from uniform. If a bunch of my p-values are basically 0, it's obvious that a bunch of the nulls in this population aren't true. So I shouldn't plug in pi naught equals 1. I could probably do better than that. Another way of saying that is if I estimate features of G, like the mean or variance or other things about it, pi naught actually can't be 1 if the mean effect is not 0, or if the variance is not 0. So for the race and gender experiments, for example, it's obvious that some firms must be discriminating against distinctively Black names. The mean effect is 2 percentage points, and the t-stat on that was 12. That's clearly a real effect. So it doesn't make sense to assume that all the nulls are true. For gender, it's also the case that some firms must be using gender, because the variance of effects was 2.7 with a very precisely estimated standard dev. Okay, so given those facts that I can clearly learn from the data that pi naught is not 1, the question is, can I do better and get a tighter bound on FDR in order to do a little bit better in my testing procedure? So we want to borrow strength from the ensemble of tests to put a tighter bound on pi naught. And the procedure for this is based on the following intuition. If I think about the density of p-values in the population of tests that I'm looking at, that's a mixture of two things, the true nulls and the false nulls. For the true nulls, I know what the p-value distribution looks like. It's a uniform with height pi naught, right? So at every point, the true nulls contribute a height pi naught to the p-value density. And then the other component of the mixture is the density for the false nulls, which is something else, which we're calling F1 of P, and it has weight 1 minus pi naught. I don't totally know what that is, but I know it's a density, and I expect that it's concentrated more towards 0 if my test is worth anything. So the false nulls should be generating p-values that are kind of skewed more towards 0 than a uniform if the test is informative at all. So because F1 is a density, it has to be the case that it's positive weakly. So for any p, you can see that this density provides an upper bound on pi naught. Okay, the density at any point is an upper bound on pi naught because at each point, that density is height pi naught from the truth plus maybe something from the false. Okay, and the tightest bound is the minimum of that density. Since every point on the density is an upper bound, the lowest upper bound is the minimum density. So that's this idea from this Efron 2001 paper. The minimum density of p-values bounds pi naught. A simple approach to that, how do I calculate this bound? If I had infinite data, I could kind of look at that distribution and just pick the minimum point. Of course, in a sample, it might not be trivial to estimate that. The approach proposed in this story article is to say, well, let's pick a cutoff lambda and assume basically all of the tests that generate p-values above that point are from true nulls. So the false nulls are almost all concentrated below lambda. They're closer to 0. If that's true, then I can just look at the total mass of p-values above lambda, scale that by 1 minus lambda times j, and I kind of get the average height of the density above that point and use that as my bound. So there's a bias variance trade-off there. The higher is my lambda, the tighter is the bound in general, because I expect fewer and fewer false nulls to be appearing in the right tail of the p-value distribution. P-values that are close to 1 should be, almost all true nulls, hopefully, if my test is working well. But I'm using less and less data to estimate the height of that density as I truncate further and further. So, choosing lambda, there's this trade-off between the noise in my estimated bound and the tightness of the bound. Story has a proposed approach to choosing that in a kind of fancy way. You could also just pick it ex ante because any lambda provides an upper bound. So you could just say, okay, I'm just going to pick lambda equals 0.5, calculate the height of the p-value density beyond that. I'm going to use that as my plug-in estimate of pi naught instead of 1 in the FDR formula. Yeah.
Why couldn't you have used your deep convolution estimate of G to back out pi 0?
So that's a great question. One answer to that is if you use a continuous distribution like the log spline thing, the answer is that pi naught equals 0. And this is not an interesting problem because there are, If it's a continuous distribution,
The null, like they discriminate weakly in one.
yeah, so you could do it that way. You could also say like, let me use an NPMLE estimate of pi naught as my plug-in estimate here. You can do that. Probably the NPMLE is not putting any mass exactly at 0 either. But it's true that as you get big enough samples, you know, the CDF of G should be decently well estimated, and you could use that. So the tradition in this literature is to treat pi naught as partially identified rather than point identified, but in principle, you could use G hat to compute it. But for most procedures, like I just said, you kind of have to broaden the definition of the null a little bit and say like what, you know, I want to look for effects that are bigger than delta for some non-trivial delta. Because if it's literally exactly 0, then it's going to be extremely hard to estimate the density at exactly that point. Okay. But once we've estimated pi naught, now we're in business because we have an estimate of the FDR associated with any decision rule, which is based on the p-value cutoff. And this gives rise to the idea of the Q value in the empirical Bayes style multiple testing literature. The Q value is essentially the estimated false discovery rate associated with the p-value for each unit. So, you know, each unit gets p-value in a classical hypothesis test. This is the Q value associated with that, which is what would happen if I use the p-value that I see for this unit as my cutoff and rejected everything with a p-value smaller than that. And that just puts a hat on the pi naught and on the F there. Okay. So this is like the empirical Bayes equivalent of a p-value. Rather than controlling the probability of rejecting given true null, I'm going to use Bayes' rule plus the ensemble of tests to flip that conditioning and control the probability that a null is true given that I rejected it. So this is just restating the definition of FDR. If a unit J's Q value is Qj, and I reject every hypothesis for units with that p-value or lower, I expect at most 100%, 100 times Qj% of my rejections to be mistakes. And it's at most because the thing I plugged in here is an upper bound on pi naught. Probably the real pi naught is lower than that. So here's what we get from this in the discrimination experiment. These are my p-values from one-tailed tests of no discrimination against distinctively Black names. So I'm doing one-tailed tests because we're kind of focused on this one-sided alternative, given what we saw in the estimated mixing distribution. We're not interested in discrimination against white names in this particular testing procedure. So this is what my p-value distribution looks like. And you can see that it's definitely not a uniform, which is no surprise because we saw that the mean effect is big. There's a bunch of p-values that are down here close to 0. There's a few in the upper tail. Okay, so the way that this FDR control procedure works is, let me pick a lambda. The example I'm doing in the slides and in the problem set that I gave you guys is just lambda equals 0.5. So instead of doing something fancy to pick lambda using the data, I'm just going to pick 0.5 and say, assume basically all the false nulls are somewhere mixed in down here. And then look at the average height of the density above this point to decide what's my upper bound on the share of true nulls in this population that I'm dealing with. That turns out to be 0.31. So at most, 31% of firms are not discriminating according to that estimate. In other words, at least 69% of the firms in this experiment are discriminating at least a little bit against distinctively Black names, according to that bound. And that means my prior, so in this expression, you know, pi naught is my prior probability that you are not discriminating. And so my prior is actually pretty aggressive based on the ensemble of tests in this experiment, because I see that it's not very likely that a randomly chosen firm isn't discriminating. Around 70% of them are discriminating, even according to this upper bound. And so I can be pretty aggressive while still controlling FDR. And so I end up using that decision rule with 31 firms that have Q values less than 0.05. So 31 of the 108 end up with Q less than 0.05. You know, why 0.05 is actually not clear. I just picked that arbitrarily. But what that means is that among the firms that are selected by this decision rule, on average, in repeated applications of this rule, so it's an expected value statement, I expect that at most 5% of the firms that receive that label are not discriminating. Okay, so 5% of 31, which is only a couple. So here are the names of the firms that are selected by that decision rule. I'll let you guys construct this yourselves in the lab, but you see we have at the top of the list, Genuine Parts, also known as Napa Auto. They have the lowest Q value in their experiment. It's pretty clear, even based on the unadjusted estimate, that effect is real. They have a contact gap of 9.5 percentage points favoring distinctively white names with standard error of 0.02. So their Q value and P value are basically 0. There's a lot of auto companies at the top of this list, it turns out. So AutoNation, Advanced Auto Parts, and O'Reilly Automotive are the next 3 in terms of Q values for discriminating against distinctively black names. And then Ann Taylor. Okay. So we saw Ann Taylor before in her context, but this is for racial discrimination. So, I should expect only 5% of firms that end up on a list like this in repeated applications of this experiment and testing procedure should actually have 0 effects. If you kind of endorse the logic of the procedure that I laid out. It's important to note that, because of this exchangeability and labels issue that we've been talking about all along, I'm not making any statements about any specific company. So I can't say, like, this procedure doesn't say Murphy USA has only a 1.3% chance of discriminating or something like that. It's a statement about the decision rule and the properties of the lists that emerge from repeated applications of the decision rule in expected value terms. So in the literature, sometimes some authors are interested in controlling more conservative notions of error than that. This is the expected value, controlling the expected value of the share of rejected nulls that are true. You could think about controlling other quantiles of that object. So it's called the FDP. So the FDP is the false discovery proportion. That is, of the hypotheses I actually considered, how many of them were actually true. And I could control the 10th percentile of that or something rather than expected value. Controlling the expected value means I'm going to do well in repeated applications across many experiments, but in any one, it doesn't say what the likelihood is that my FDP is reasonably low. So it's kind of important to keep that in mind when we do this. Okay, this is actually the last piece of this. So I got through the non-parametric EB faster than I thought, but I'm going to give you a kind of twist on this multiple testing idea to end the lecture, and then we'll spend the last chunk letting you guys work on some multiple testing and non-parametric EB examples from the data set. But this part is based on a new paper that was with the genesis of us releasing the names of the companies. Actually, we just put out this paper with the names in it. Yeah.
So, well, I wonder how much pushback you got for this, but at the end of the day, how did you choose the end for this experiment? So each of these numbers ultimately comes from 8 resumes that were sent.
These numbers each come from about 1,000 resumes.
But to each of these companies, only 8%.
No, 1,000.
Oh,
8 per job, 125 jobs per firm.
Oh, okay,
Yeah.
sorry. So 8 per job. I see. So it's 1,000.
It's about
Why did you choose that number?
So we were interested in understanding the heterogeneity in companies in this discrimination parameter. So we basically did a power calculation for the variance of the mixing distribution. So like sigma theta squared is the target parameter. How much precision do I need in order to reliably detect sigma theta squared is not 0? So instead of a power calculation for the mean, it's for the variance.
Reject, there's no heterogeneity.
Yeah, that was the power calculation that we did. I mean, we knew we were going to do like this part. This was in the pre-analysis plan also. So we knew we were going to do more stuff with it, but that was the target parameter, and we wanted to make sure we were powered for that. That makes sense. Okay. So this paper is about ranking problems rather than multiple testing, but it has a lot of similarities to the stuff we just went through. In these types of value-added studies, where we have many unit-specific parameters, it's often natural or very tempting, at least, to focus on who ends up at the top of the list versus the bottom. I kind of did that on the last slide, for better or worse. It's, you see a list like this, your eye is drawn to the top of the list. So the second paper is kind of about how should we construct lists like that in view of that issue. Okay, Gu and Conker have some really interesting work on empirical Bayes tail selection problems. They call this the league table mentality. We're all about constructing these league tables and scrutinizing the highest and lowest performers. And more broadly, we have these report card classification systems that are popping up both in the academic literature and in the policy world. Report cards for schools, which schools are doing well, not so well, college report cards, the neighborhood kind of opportunity atlas. You could think of that as a report card of this form. What are the highest mobility neighborhoods in the United States? Those are sort of rank ordered lists of the best and worst performers on some dimension. And the issue we were trying to deal with in this paper, which is very closely related to the multiple hypothesis testing problem, is that comparisons like that can be hazardous due to selection on noise. If you make a list of theta hats, you order the firms by that, the one at the top is almost certainly, on average, going to have positive noise in it, right? So I'm selecting on a noisy estimate. I expect that the estimates at the top of that list are going to be overstated. The estimates at the bottom are going to be understated for the exact same reasons that we've been talking about shrinkage along the way. So if I'm specifically interested in rank ordered comparisons and I want to worry about this problem, what should I do? There's a recent literature that's been really focused on this in view of the increasing prevalence of these types of systems in the empirical literature. Andrews and co-authors have this paper on inference on winners. So it's like, I'm going to select the one at the top of the list. Given that I'm doing that, how should I do inference on that parameter to kind of bias correct the fact that it came out of a procedure that selects partially on noise, and I would have done something differently, if this one hadn't been the highest one on the list. Another slightly different approach to a similar problem is this paper by Mogstad and co-authors, which is about treating the ranks as unknown parameters. And so there's some real ranking of the units on the true thetas, and let me just form like a confidence region for those ranks and do inference on the rank. So can I reject that the rank for this one is less than the rank for that one, and so on, in a kind of classical hypothesis testing setup. A slightly different approach that we pursued in this paper was to think of the relative comparisons across the units as a decision, and think about what type of loss we hope to minimize when we make comparisons like that. So if I'm forming a report card, my decision to place one firm above another, that's a choice, and that might be wrong, and I pay a cost if I get that choice wrong. So if I formalize that, what's the optimal report card to make my loss as small as possible? So that was the idea in this paper, and we did this for the discrimination experiment example. In particular, we're constructing discrimination report cards. And we started basically with this loss function, which hopefully captures some of the intuition underlying this league table mentality type of reasoning that we're seeing in the literature. So this loss function says, I have a decision delta 1 through delta j, which is going to be like a list, okay, of firms, numbers 1 through n potentially, but I can have ties if I want. So I report a number for every firm. And my loss associated with that report, delta, if the true parameters are theta, is going to look like this. There's j choose 2 possible pairwise comparisons between firms that I could make. Okay. So if I'm thinking about all the firms that were in the experiment, I could pick any 2 and compare them. So I'm averaging what's going on across all those pairwise comparisons. And the loss says, if theta I is actually bigger than theta j, but I said the reverse, I get loss 1. Likewise, if theta I is less than theta j, but I said the reverse, I get loss 1. Okay. But if I say the right thing, I get a bonus of lambda. which this is loss, so it's minus lambda. Okay, so this is the average of this quantity here, which says if theta I is bigger than theta j, and I got that right, I get a bonus of lambda. Okay, and then likewise for theta I less than theta j. And then you can see in here that if delta I is equal to delta j, that means I throw up my hands and I didn't make a comparison and everything drops out. That loss of that is normalized to 0. So it's like I lose 1 if I get it wrong, I gain lambda if I get it right, and I get nothing if I refuse to play. Yeah.
So is it constraining here the fact that you imposed that you're ranking everything out of order? Like,
Yes.
could you have done something where you're like, A is better than B is better than C is better than A? It's like totally unconstrained.
Yes, it is. And in fact, that's exactly how we end up implementing this. So you could think about this as a choice for every pair. I can make a decision of should I be better than J be better than I, or should they be tied? And that's a 3-dimensional choice for each of the J choose through 2 pairs. I could just solve the unconstrained version of this problem and choose that very high dimensional decision vector. The way we did it was impose transitivity constraints, which projects it down to a 1-dimensional list. So if I rank I above J and J above K, I have to rank I above K. I'm not allowed to have cycles in my rankings. You don't have to impose that, but then the output of it is very hard to summarize and kind of weird to explain to
I was
anyone.
wondering if that is really I would think it'd be weird if there are too many of those. So I'm wondering like really how binding is it to impose that it has to be a ranked list?
No, this is a very astute question. We have some metrics of how binding the transitivity constraints were. I didn't put them in the slides, but it is that was kind of the animating force underlying the way that we thought about this actually. So this is my loss function. I have discordances that give me loss 1, concordances that get me gain lambda, and then ties that get me nothing. To interpret this, I can rewrite that function like this. So it's minus lambda times something called tau, plus 1 minus lambda times something we're calling dp. What's tau? Tau is Kendall's tau measure of rank correlation between the decision that I make, the delta, and the true theta. So Kendall's tau, you could think of that as the concordances minus the discordances averaged over all the pairwise comparisons. So you took the lambda off this would become like Kendall's tau. So basically we added and subtracted to do that. And then the part that's left over is the discordance proportion, which is the share of the J choose 2 pairwise comparisons that are strictly misordered. Okay. So what this means is that if I choose this preference parameter lambda to be equal to 1, this part goes away, and I'm just trying to maximize rank correlation between what I report on my report card and the truth. And that actually implies that I won't coarsen, I won't create any grades at all. I'll just report my best guess as to the true ranking. That's my way to try to maximize Kendall's tau. Okay. When lambda is less than 1, there's kind of an extra kick coming from the mistakes that says I care about making mistaken pairwise comparisons on my report card list over and above the degradation in rank correlation that comes from those discordances. There's an extra penalty for a discordance, which we called in the paper discordance aversion. Okay, so if you think about it, having that kind of force in the model says you have an incentive to avoid such mistakes by coarsening and declaring ties. Okay, if I send lambda towards 0, I really care about discordances. And so I'm only going to assert that I is better than J if I'm really sure about that. Otherwise, I want to create bins and just throw up my hands in those bins and not declare any grades either way. So of course, so what I want to do is minimize my loss. Of course, if I knew the thetas, I could make tau equal to 1 and dp equal to 0, but I don't know the thetas. So what I have to do is minimize expected loss, aka risk, which is given by this expression here. So the best decision rule in this problem is minimizing minus lambda times average tau, where this is like integrated over theta, plus 1 minus lambda times dr. So instead of dp, it's dr. That we chose that language because of this analogy to the false discovery rate type testing literature. You know, the FDP, as I said before, is the false discovery proportion. That's the number of actual thetas that I get wrong. The discordance rate is the average of that across repeated applications of the decision rule. So the risk and the risk minimizer is going to use that. Okay, so tau bar is my expected rank correlation given the distribution I'm facing from reporting delta. Discordance rate is the expected proportion of discordances given my decision rule. And you can see here that averaging over G, basically, the mixing distribution, which is what my expectation operator is doing, is turning the indicators for theta I bigger than theta j and so on into probabilities that those events are true, which tells me that the decision relevant functionals of the posterior distribution in this case are pairwise probabilities that theta I is bigger than theta j given the estimates for those units. This should have a hat on it also. Okay, so I have estimates for every pair of units. I do deconvolution to get my G. I can use that then to compute pairwise probabilities that each theta exceeds every other theta. Those are my pi's. And the empirical Bayes approach is to plug those pi's based on the deconvolved G hat into this risk function and minimize risk by choosing my delta. Okay. You can see, related to the discussion we were just having about transitivity, if I only had 2 units, it's pretty clear based on these expressions that what I should do is rank from I above j if that posterior probability exceeds 1 over 1 plus lambda. Okay, so if lambda were 1, if we were weighting discordances and concordances equally, that's 1/2. I do the reverse ranking if pi ij is less than lambda over 1 plus lambda. Again, that's 1/2 if lambda is 1. And I declare a tie otherwise. So what that says is as long as G is continuous, if lambda were 1, I would just say which one is more likely. That's the one I pick. If lambda is less than 1, there's a region in between these two numbers where I'm not willing to make an assertion about which one is bigger than the other one. And I declare ties. So if I were doing it unit by unit, that's the solution to this problem. But that can, in principle, generate, it's very closely related to Condorcet cycles in kind of voting problems. You can get cycles in the rankings where you're willing to rank I above j and j above k, but not I above k, and so on. And we actually had some Condorcet style cycles in our data, primarily based on ties. So sometimes you want to make I tied with j and j tied with k, but k bigger than L, and then L tied with j again, that kind of thing. Okay, so we plug in EB posterior probabilities pi hat. We impose the transitivity constraints that make the ranking obey one-dimensional ordering, and then we have it output our report card for discrimination in this experiment. So this is what that looks like. There's a lot going on under the hood that I'm not going to show you in the interest of avoiding tedium. But briefly, what we did here was we did a deconvolution procedure where we estimated the mixing distribution across the thetas in the experiment. Based on the previous paper, you could see that there's a ton of action in industry in this experiment. So like all the companies at the top of that Q value list were auto companies. And that was true more generally. Industry explains a big chunk of the variation in thetas, both for race and gender. So for this version of the deconvolution, we actually built that into the procedure and condition on industry. Think of that as like a covariate. When we built the posteriors, which generates a lot of extra information. So this comes from a model that has industry effects under the hood. We have another report card that doesn't do that, but this is kind of the fully informative report card. And what I'm going to show you here are essentially the grades that come out of this for racial discrimination, where I'm setting lambda equal to 0.25. So that's relatively conservative in the sense that it means the bonus that I get for getting it right is only a quarter of the cost that I pay for getting it wrong. So I have a lot of incentive to declare ties and kind of avoid making any assertions. I have to be quite sure. I have to be in the pairwise problem. I have to be like 80% sure in order to make an assertion with that loss function. So these are the 1-star firms. So, we, instead of a giraffe, we made these stars. So you get 1 star if you're in this bin. Those names should be familiar from the Q value table. So this is a different objective. This is about pairwise rankings, not about testing for theta equals 0, but the two things are kind of related, and it turns out that the companies that get at the top of the list in the two procedures are highly overlapping. So the 1-star group for racial discrimination, AutoNation, CVS, Advanced Auto Parts, Genuine Parts, which is Napa, a couple other car companies, Disney, O'Reilly Automotive, and VFC, which is North Face. Second group has Ann Taylor, Rite Aid, Pilot Flying, and so on. I'm not going to read them all. And then we have kind of a big group in the middle where we can't say much about pairwise comparison. So the algorithm wants to kind of bin all these together and just say, like, we're going to treat that as the middle group and not compare them to each other. And then we get this group at the other end that this loss function thinks is pretty clearly distinguishable from the ones that are up there. So these are kind of the ones that are doing the best, according to this. So that's another virtue of this kind of decision theoretic approach to the problem, is that for when you're doing testing, you just say, I reject the null or I fail to reject. And if I fail to reject, I'm just not going to say anything. This way of doing it, we have a bin at the other end, which says, like, we're pretty sure these ones are doing well, in the sense that the pairwise comparisons between these guys and these guys are very likely to be accurate. Yeah.
So how did you do the groupings?
How did we group them together?
Well, you're grouping into 4 buckets. So
That's an endogenous output of this risk minimization problem. So before you turn on the machine, you don't actually choose anything about the grouping. You just choose lambda. You get your mixing distribution, you plug in your posterior probabilities of all the pairwise orderings. You choose how much you care about getting it right versus getting it wrong, and then you press go. And it decides who should be in what bin and how many bins.
sorry, I didn't understand how it does that. Figures.
That's
The pairwise thing, but how
well,
does
it has to come up with the solution to this delta is a list of numbers that can be tied. And so the solution could have a bunch of ties in it, and it does. That's what those bins mean. The bins are ties.
So everybody within a bin is indistinguishable from one another.
The algorithm says that given your loss function, you shouldn't make an assertion about those companies relative to each other. They're not distinguishable enough to be worth it.
But it does not mean that if you take like 2 neighboring that are in different groups, you can reject they are different, right? Like that would be a different test. Like if you take like 2, like the border between 2 groups, you can't reject. It doesn't mean that you can affirm that they are different, right?
Not quite, but you can compute based on the G, the probability that a randomly selected firm in this group.
Yeah, random select, but not at the border.
Not at the border. Yeah, the border is arbitrary. We ordered them by, I think, their ranking under lambda equals 1, which has no course name, which you can see is these dots are the posterior means. So it's kind of monotone, almost monotone in the posterior mean, but not quite. The lambda equals 1 ranking. But you can say that's the analogy to false discovery rates. You can do like a directional false discovery rate for this versus this. If I assert that a randomly selected company from here is not as discriminatory as a company from here, how often am I going to be wrong about that? You can estimate that and report that. So we have that in there. Okay, so at this end, I find this to be an attractive feature of this type of approach to the problem, because we get this list of companies that are doing pretty well. This is like Charter Spectrum, Kroger, Dr. Pepper, Avis, Mondelez, Waste Management, Cisco, Kohl's, Publix, ACOM, Ryder System. So those companies are, according to this algorithm, kind of belong in a bin at the bottom and are discriminating the least on the basis of race. We don't know why, but it's a potential area for further scrutiny. If we were just doing hypothesis testing, it's a little bit harder to say what to make of a failure to reject. So here's the gender report card in case you're interested. This is, again, using the industry effects. Turns out that the algorithm puts one company on its own at this end of the spectrum, which is going this way, we're seeing more discrimination against women. So this company was kind of in the tail of discrimination against women in the experiment, they get their own star category, turns out, according to the algorithm. Again, we didn't pick that. That's what the integer linear programming routine tells us. There's two companies, LKQ Auto and Honeywell on the next bin, and then there's a bunch of firms that are in the middle. And that's sort of consistent with the mixing distribution I showed you. You know, there's a lot of mass near zero, and then there's these tails that are way out there. So it's sort of finding those and giving them their own grades, and everybody near the middle, it's saying like, we're not really sure who's who, so we're gonna make that a single mediocre grade in the middle. And then down here, we have these other companies, which includes retail, a lot of retail companies, so Gap, Victoria's Secret, CBRE, I think that might be Ann Taylor. I forget what that stands for, but I think that's the company underlying that.